theory is given by the formula over here. Not sure if one can show well. Anyhow, is there a pointer? No. Okay, that's fine. That is given over there, and all the properties that entered in this formula, in particular the free energy barrier for nucleation, can be calculated from the simulation. And the simulation consists in carving out, inserting an approximately spherical ice cluster inside a big water simulation in order well, I don't know. Anyhow, let me, sorry. Well,
it doesn't show on the, it does show. It doesn't work on the.
It doesn't show on the screen.
Yeah.
That's fine. The point is that, and then one sees after one let this cluster equilibrate, and one sees whether the cluster keep growing or keep reducing its size in order to determine the critical cluster. The critical cluster has a number of molecules given by NC in the formula over there. And delta mu is the free energy difference, or the difference in chemical potential between the liquid and the solid. That has also been calculated with this approach for different levels of undercooling. And the smaller the undercooling, the bigger the cluster one needs to simulate. So for the smallest undercooling that we were able to model, we needed a cluster of approximately 10,000 molecules that was embedded in a liquid with of the order of 100,000 molecules. So this to give you the idea of the simulation that one can do with a scheme that has retained the accuracy of DFT. Now, this is the result for the homogeneous nucleation rate compared with empirical potential like the T4P ice, which is one of the best empirical potential for the system, compared to experimental data, and compared to the MW potential, that is a potential that does not include, is a coarse-grained potential that does not include the hydrogen. In the description is a formulation of the Stillinger-Weber potential for water. And you see that the nucleation rate varied by many orders of magnitude, and the error bar associated with the calculation is approximately with this approach is approximately 10 orders of magnitude. But still, it is quite amazing that one can predict with remarkable accuracy, I would say, within the error bars. The results are consistent with the experimental data. The dashed line is the threshold for the is the homogeneous nucleation line that is predicted correctly by the approach. And I will not discuss much on that on the right-hand side, but the right-hand side shows that there is correspondence between the surface, the interfacial free energy that is calculated from the classical nucleation theory and the direct calculation of that at the melting. If we extrapolate the result of classical nucleation theory that are given by the green dot with error bars to zero temperature supercooling, one obtains an interfacial free energy that is perfectly consistent, is very close to the one that we predict with explicit simulation, in which we crystallize and recrystallize and melt reversibly a layer of ice for different surfaces, prismatic, secondary, prismatic, and basal, and various surfaces for the system. So this shows that this kind of simulation can be done. And also, we used a very simple model to introduce stacking disorder in the system, and we see that this increases the rate, improving the agreement with the experiment. So I will, this is enough for this particular application. Let me move to the next one that is quite interesting and involves another development in the deep potential methodology. Basically, we want to model, we need to model also the dipole of the simulation cell or the polarization. And that is given in terms of the dipole moment of the atoms and the dipole moment of the maximally localized Van Allen center. So in order to be able to model the polarization, we need to model how the maximally localized Van Allen center depend on the environment, and that can be done again with a formulation similar to the one that I described before for the potential energy surface, with the only difference that now the function f is a vector function and before it was a scalar function. So in this way, we can model the polarization, and we use that to describe the ferroelectric phase transition in lead titanate. Now, lead titanate is a prototypical ferroelectric material, and here I show the tetragonal unit cell of the system. At low temperature, the system is in the ferroelectric phase, the symmetry is tetragonal. At high temperature, the symmetry is cubic, and one is in the paraelectric phase. Experimentally, the phase transition is first order and occurs at 663 Kelvin. Using the deep potential scheme for the potential energy surface and the polarization, the transition can be studied with molecular dynamics. Now, there is, one has to realize first that SCAN-DFT, even though it's a rather accurate functional, is not perfect, and it makes a significant error. It overestimates the tetragonality, which is the ratio C over A for the system. And you can see the comparison of the tetragonality calculated with the deep potential model and experiment, that is the black line here. So this would indicate a transition that occur at a few hundred degrees higher than experiment. In order to reduce the tetragonality error, we used a simple fix-up that was suggested long ago by David Vanderbilt and Karen Grape, which consists of applying an external hydrostatic pressure to the system, and we fix the hydrostatic pressure in order that the tetragonality of the system coincide with the experimental one at 300 K. And then we can see that in this way, the result of the simulation for the various lattice parameter becomes much closer to experiment. And we can also see that there is a dependence on size. We have a very good convergence with respect to size with L equal 15, already with L equal 12 is very good. So L equal 15 means 15 to the cube times the unit cell. So it's a rather large simulation with more than 10,000 atoms that one need to do. Now, having this scheme, we can calculate various properties. Here I show the enthalpy compared with experiment, refer to the enthalpy that would be predicted by the Dulong-Petit law, which is something that both experiment and the simulation show at in the high temperature phase. We can compute the specific or the heat capacity and simply by the fluctuation of the enthalpy in the simulation. And again, we see result from the theory and from the simulation, and from the theory and from experiment. And we see that there are some differences in experiment that likely are due to the different amount of defects that are present in the samples and that are prepared with different technique. We can also look at the spontaneous polarization, at the pyroelectric coefficient, and at the longitudinal susceptibility, which is calculated from the fluctuation of the polarization. And and again, we have rather good agreement with experiment, and all these properties are very close to the experimental prediction. But having the simulation allows us also to say something about the phase transition. The phase transition is first order is already apparent from the plot that I showed, but this is can be seen also here in the plot of the Landau free energy profile as a function of the magnitude of the polarization. You can see the yellow line correspond to the coexistence. We have two basins, a basin that corresponds to the ferroelectric phase and a basin that corresponds to the paraelectric phase. Now, having determined the two basins, we can also study the distribution of the dipole, of the unit cell dipole. And we see that the distribution of the unit cell dipole at a temperature of 820 K, which is the temperature of the phase transition with a size equal to 12, L equal 12, changes little going from the para to the ferroelectric phase. So it means that the local dipole are still there, and the transition is driven not by a displacive soft mode, but is driven by order disorder. So that is, again, something that we can get with this simulation. Another thing that we can get, and on which we are working now, because we want to develop a model derived from the basic microscopic theory, is to derive a field theory model that will allow us to describe the system in mesoscopic scale to study domain wall dynamics. And here was just the first step that shows that we can fit quite well the result of the simulation. Now the free energy surface as a function of the vector polarization, we can fit quite well in a range of about 300 K plus or minus the temperature of the transition with a Landau-Devonshire theory given here. And so this is just to say that this is something that one can do. And I want to just mention that the result after we do the fitting, we get that indeed the parameter alpha 1 depend linearly on the temperature as predicted in the simplest Landau-Devonshire theory, while alpha 11 and alpha 111 are approximately constant. And that comes out without having assumed that, but just as a result of the simulation. Now, let me go to the last, to the very last example. This is important because so far I've used model that are based on this local representation. But the local representation and the extensivity may fail. And in fact, it fails when long-range electrostatic interactions are important. And that is what we have introduced in the deep potential long-range model. And now let me show just one result that is very nice, was obtained by Chuni Zhang and Shifan Wu at Tempo. And this is in liquid water, the dipole correlation function that is important to calculate static dielectric constant. This simulation were done at 330K, classical simulation. And the 330 accounts approximately for the 40K difference in the melting temperature of the system compared to the real water. And what one can see is that if one computes this correlation function with the deep potential model, it shows an exponential decay. We could go to very large system size, up to 100,000 and more molecules. And instead, if we use the deep potential long range that include the electrostatic long range interaction, it goes to a constant that scales a constant that scales like 1 over L to the cube, which is what it should be according to theory because of the dipole-dipole interaction that decays like 1 over R cube. So calculations that do not include this effect are not correct, although the results are not very different overall, but they are not correct. And in particular, they don't give consistency within different boundary conditions that one can use for the system. And this is just to show, but Shifan has also some additional data on that. This is just to show the result for the dielectric constant that one obtained with this model at 330K using both the metallic boundary condition, that is the one typically adopted in supercell calculation, and using the Kirkwood-Fresh boundary condition that we can also impose because we can do these very large simulations sizes, and we can see that both condition converge to the same result for the dielectric constant that is overestimated compared to experiment. Well, I've been rather quick, and so now it's the time to go to the conclusion and outlook. So, molecular dynamics with machine learning potential retain the predictive power and accuracy of ab initio molecular dynamics with numerical efficiency comparable to that of empirical force field. Relative to empirical force field, the potential and the potential long range describe accurately interactions beyond few body interaction. Moreover, the potential are reactive and can describe formation breaking of chemical bonds. One can envisage, as I've shown in this talk, a hierarchy of coarse-grained models that are derived bottom-up. The first one is the deep potential in which the electronic information is eliminated. The second one is the deep potential long range in which the long-range electrostatic interaction is retained by retaining information on the Wannier center, so by retaining information on the electronic structure. And then there are mesoscale models that could do additional coarse graining. I just mentioned an example in the case of the Landau Devonshire model. One important limitation of the current approach at which we are working, and we're making very good progress, is that we have a constraint on the fact that the Wannier center are uniquely associated to the atoms. Now, what we would like to do is to describe Wannier center that can describe also unpaired electrons, like one can have in a solvated radical or in a polaron. And that requires some additional technique, but we are getting there. So that is very nice, because that will allow us to describe the dynamic of a chemical reaction in which we can see what the electron do. At the moment, we can only see chemical reaction with this approach, with the Vanier center, chemical reaction related to proton transfer, but not electron transfer. Finally, machine learning models like the deep potential reproduce the DFT reference with better than chemical accuracy, but typical DFT approximation are not chemically accurate. But in spite of not being chemically accurate, are pretty good, as we can say, because they describe very well the trends and the qualitative feature. Now, a big question mark is how can we improve on that, and that I leave to you. Okay, thank you very much, and I'm ready for questions.
Thank you, Roberto, for this very nice talk. Do we have questions? First in the audience. So we have a microphone that's coming.
Hi, how did you compute the Landau energy surface in the unstable region? In the unstable region where it wants to phase separate. Yeah.
We use, when we compute the free energy surface, we use wet dynamics with factor that allows the cross the barrier very small, but it's very small because it is related to the unit set. As we go to the after set, the barrier increases, and in fact, there is a very interesting thing of the barrier when it comes to study then the dipole distribution and understanding that I was able to think that the barrier in a first order phase transition should increase in size like a surface, because typically the system is created by the interface, the smaller possible size of the interface. So the barrier should go like what we get from this simulation is that the barrier actually goes like the volume. And the reason why it goes like the volume is that the entropy is dominating due to the disorder that one has in the order disorder transition. The entropy dominates, and it's something that occurs at the level of the unit cell. So the unit cell has a dipole, but this dipole gets completely disordered as we cross the phase boundary. And in this case, the entropy increases like the volume. And so this gives a barrier that increases like a volume. In fact, I think that a correct statement is that in a system that undergo first order phase transition, the various thermodynamic properties scale like geometrical properties, whereas if we are in presence of critical phenomena, there are critical exponents that do not obey the geometrical property. The geometrical property is present over there and is related, is another signature of the order-disorder transition that dominates the system. Quite interesting in the past, and I was used to think like that, in the past, the system was considered to be a prototypical example of a displacive transition. Although I must say that David Vanderbilt, who studied this system quite well, already hinted at the fact that order disorder could be quite important in this system. So that's what I would say regarding to that.
Thank you. Very interesting.
Okay, yeah, thank you so much, Roberto. We're already running out of time. So let's thank the speaker again for this nice talk.
Thank you very much.
Okay. Okay, perfect. So let me introduce our next speaker. She's Nong Atrid from University of Utrecht in Netherlands. And she's continuing in the machine learning session to talk about machine learning topics. So she's talking about machine learning potentials for accurate and efficient atomic scale simulations. So we're excited for the talk.
Oh, excuse me, can I take the microphone?
Yes. So you either use this one or you want to
I
use
can
this
use this one. Why my screen doesn't show? That is good. Okay, hello everyone. So you can hear me well, right? Yeah, sorry for the technical problem. But first of all, thank you very much for the kind invitations to invite me to join this ES 2022, which is very nice. And also thanks for the first speakers that already give very nice introductions about the methods and about the topic that I'm going to continue to discuss in my talk. So as already in the titles, I will talk about machine learning potentials to accelerate atomic scale simulations, which is our group. We develop our own machine learning potential software package, the Atomic Energy Network. And also after we develop the database and also machine learning model, we also share our database and machine learning model with the scientific communities, like you can see here. But before I talk about the research, I would like to thank our collaborators and also the facilities. Because of some of the work that I will discuss today, this is in collaboration with, for example, Professor Gerben Saders from Berkeley, and also Professor Urbans and Columbia, and also some of the projects from Professor Kainas and also Dr. Cooper from Stuttgart, and also the current project that I also will briefly discuss. This is in collaboration with the Columbia Center for Computational Electrochemistry, or CCCE project, which is started since 2019. I will slowly walk a little bit from the beginnings or the principle before I show, or even Professor Carr already show how fancy and also how powerful of the methods and the models can do a lot of applications. So basically, we are developing a machine learning potentials, for example, to address the complex, in my case, this is complex materials by, for example, learn from accurate electronic theories on the methods, for example, like a DFT. So I would like to mention that the hardest part also how to get really reliable and also accurate the reference data, for example, a quantum mechanics database or even DFT database. And then use this accurate and also reliable database to interpolate and construct efficient and also continuous machine learning models, and then use it in applications, for example, in MD simulations or Monte Carlo simulations. So our group, actually, there are so many different machine learning models, but we use artificial neural network for the interpolations because it's can only simple to use atomic positions and also the energies and also some easy information that we can use it as a reference, and also can really highly accurate represent or can fit or train to your reference database like DFT, and also reactive and also full dimensional. As I already mentioned earlier, I would like to go a little bit in the principle what we did. For example, here, how neural network fittings look like. For example, in this, on the left-hand side, this is a water dimer, like you can see here. The DFT reference data in the diamond symbols and also neural network fittings in the red a solid line. And in the same time, you can also use the same neural network models to train more complicated. For example, in high-dimensional structures, in this case, I use like a copper gold crystal structures or alloy. And also the same on the right-hand side, we have the symbol as a reference, the DFT data, and also the solid lines as a neural network fittings. So after a few iterations, you can see that neural network can fit or can train and can represent the DFT reference data very accurately, both molecular system and also the crystal structures like you can see on the left-hand side. So this means the NN potentials can establish a functional relationship between the structures and its energies. So basically that there are so many ways to describe. And for example, we are working with a very complex or very complicated materials. For example, like the interface, like a gas-solid interface, or even the solid-solid interface in our own applications. So we make use of the method that developed by Baylor and Palinellos in 2007 with the high-dimensional neural networks. And the important part in the development in that time, this is how to get accurate energies or total energy is come from by looking at convert or transform the atomic position to a local environment, which it is called some community called fingerprint, which is fingerprint are the sets of many body functions that describe the local atomic environment of each atom. So for materials that we are interested in, so a radius cutoff around 6 to 8 angstroms already good enough. But if you are looking at like a gas phase, maybe you need a larger cut, maybe 12 angstroms or 15 angstrom cut, for example. So basically, I will just skip this because Professor Ka already mentioned that the good descriptors has to follow the invariance of the energies. For example, it has to get the same, even you have the same atomic positions, but you have a transform or rotations, the energy should be the same. And this is make our descriptors is powerful and can use to any type of structures or any system. And not only that, each NN also has two specific number of the input nodes, and also the descriptor of atomic environments must also have the constant dimension. So this is very important because of when we work on very complicated system, if we have efficient and also accurate descriptor, also will help us to evaluate our machine learning models at the end to get to capture the accuracies of our database. This is the with list of the descriptor of local atomic environments that we have. For example, that it should not require too many human manual to adjust the parameters. And also the resolutions of accuracy should also be systematically verifiable. And the algorithms should also very computational, very efficient. And the computational cost should not be independent of the number of chemical species in the atomic structures. So we proposed and we extended the method by Bailey Palinellos that proposed in 2007 by expand the coefficients that projected to the radial distribution functions or the RDF and also angular distribution function ADF by introduce the orthogonal expansions and also introduce another type of the descriptor. It is called spatial weight parameter, which is to classify different type of chemical species. For example, here we introduce the Chebyshev polynomials to expand the coefficients. Like you can see here, A and C figures. This is our descriptor to describe atomic structures. And then we introduce or expand the coefficients with the order of Chebyshev polynomial expansion. And then we introduce a second set of the descriptors that we can have many more different type of chemical species. So we include introduce, if you have one chemical species, we introduce the weight type of the chemical species by having the W here weight type as a 0. But if you have two chemical species, you can introduce the integer number like -1 and +1. And if you have 3 chemical species, you can introduce the W or weight type like -1, 0, and +1, for example. So in this case, it really make our descriptor is really very efficient. And maybe the cartoon look a bit complicated. Maybe it's easier to take a look at the equation, like you can see here in the slides that we have. This is by have the RDF and also the ADF, and then introduce many different type of chemical species by introduce the weight type, like you can see here. And the expansion of the coefficient is become 2 in this term in the slides that I can show. So now our descriptor has 2 types. This is the descriptor to describe atomic structures and also the descriptor to describe different type of chemical species, and make it easy to use it for many different type and very complicated system. So we test with with many different type of structures. So in B figure, you can see that we look at the solid oxides, for example, the lithium tensylmetal oxides structures that we get the database from material projects. You can see that we increase many different type of chemical species, and our aim and predict the energies very close to DFT, like you can see in the figures. And not only that, we also take a look at the database with the complex molecules. We also get the database from the NOMAD, which is a database. This is a amino acids complex, which is from ABJ Ames. The accuracies of our ANN predictions with the Chebyshev polynomial descriptor also give very good agreement with the FT reference data. So far, I only discussed, we only train our ANN potentials with the energy only. But sometimes we also need very accurate forces that we will use is for MD simulation. But most of the time, if we use all of the forces components in the training set, the computational is also very expensive. So we propose to use maybe atomic forces include in the training set via Taylor expansion. As you can see here on the left-hand side, so usually if you would like to construct a very accurate ANN potentials, you need to increase a lot of number of data points if you only use the energy training only. Like you can see on the left-hand side here, if you have only 500 DFT data points, this is the absolute errors that you can see of the forces. But then when you increase many more data points, like 2000 structures, so the forces is improving, right? But and also another visualization that you can see here, you have more data is also give quite good agreement. And this is how many scientists also starting. We only use the energy training only. But as I already mentioned that sometimes using the forces also very complicated. Then we test our propose that we try to use the force which it approximates as energy via Taylor expansion, like you can see in this equation, by introduce a small atomic displacements. So we test as a benchmark here as a carbon dimer. On the left-hand side, you can see it's only energy training only. The blue is the DFT data points, only these 7 data points. And the target is the energy curve. So after a few iterations that we fit the ANN, you can see that the ANN fit give slightly different the distance that it should be at the minimum distance. And also the energy also predicts slightly not very accurate. But then we introduce our new methods by including more information via Taylor expansion. And then we use the same ANN and train and fit. So the approximate for training improve our ANN potentials. And you can see that actually it's also depending on the system that you are working on. In this case, we work with water clusters. You also have to try to find what could be the maximum random atomic displacements in your system. So in this case, for water cluster, so the displacement around 0.01 angstrom or 0.015 could be the best because give the lowest RMSE or absolute errors of the forces. And also the more data points that you include is also improve our ANN training. As I already mentioned before, right? If possible, using direct force training give really very good prediction. But as you can see that for our water cluster, the CPU time, if you compare with the direct force trainings, it use 8 times more CPU time than the Taylor expansion methods. And in my own work, we are always working on the condensed matter or really like the interface, for example, solid liquids or solid interface, which is really very hard to use all of the forces components included in our training set. So we did another benchmark and take a look at this rock salts cathode materials for lithium ion batteries. As you can see on the left figure, we also, again, try and also really vary what could be the best, the maximum displacement for this system. So we found that the optimum displacement is larger than for water, which we found that is around 0.02 angstrom. And also include a bit more of the new type of structures in the training set, also improve the force information that we can get it there. So how can we trust that this is really can be a good ANN potentials? So basically, we test our benchmark or our models used in MD simulations, like you can see here. So in this case, only the 800 DFT data points, and we only use energy of the 800 DFT data points and train many different MD simulation, only energy only. So sometimes our MD simulation also explodes very early, and sometimes it's also not very stable. But most of the time when we use the force information based on the Taylor expansion, make our MD simulation quite stable. So this is just show as a benchmark. Yeah, so basically just to summary how we construct ANN potentials in practice. So we need to have like a good initial reference DFT data, and then we select the DFT or the data that we want to use it to construct ANN potentials. And then we start to select the model selections and then model training, and then start to validate our ANN potentials. But if it's already good, then we can use it to our own applications, for example, in MD or MC simulations. But if our ANN potential is not good, then we include another type of the features like active learning to make sure that you have a good ANN potential for your own applications. But this is maybe it's very abstract. I just show you one concrete example. For example, here we have initial the DFT reference data, and then we construct the preliminary ANN potentials, and then we use this in MD simulations, and then we start to compare our ANN and DFT along MD trajectories. And if the ANN predictions is quite high or large errors, and then we have to include them include in the training set, because this means they are not in good agreement or not included in the training set already. So we do this like iterative refinements until you get really good ANN potentials. And we implemented those methods in our atomic energy network. If you are interested in, this is the references that you can take a look. We also test that ANN model that we have can also work with any kind of high performance computing systems in the US and also in the Netherlands. And also thanks to our collaborators, we also develop many different type of features right now, but hopefully one is done and we test, and we also will share with the scientific communities. This is one quick example that you know that running the MD simulations sometimes is also take a lot of CPU time to get the result as accurate as experimental measurements. For example, in this bulk water, we would like to take a look how to convert the water diffusities. So having efficient and accurate ANN potential for water, this is important. And not only that, we also test with many different types of material systems. In this case, also amorphous lithium silicon. And you can see that using many different nodes, even in this example, around 1 million atoms, is only take around 15 seconds on, for example, 96 CPU cores on the Columbia supercomputer here. And if you increase many more core or many more nodes, it's only lost like a 20% efficiency. And yeah, a few examples, if I have time, I also will briefly show that we develop database and also machine learning models based on ANN potentials. If you are interested in, I will be happy to discuss and share our database and machine learning model with you. We also support the ANN users. They also use and also apply to their own research problems, like you can see here. And briefly to discuss, once we already construct efficient and accurate ANN potentials, we could really simulate such a complex and large systems like realistic, like experimental scales like this system. This is a copper zinc oxide. This is a good catalyst for methanol synthesis. So we develop ANN potentials and then set up the model is around 8,000 atoms, and then use in MD simulations around 1,000 Kelvin. So the objective is that we would like to understand how the interface look like between the copper in orange and also zinc oxide here. So in this case, we found that after around 300 picoseconds, so we already could simulate our copper zinc oxide, similar structures like in experimental scale, like you can see on the right-hand side there. And not only that, we also test and help our experimental collaborators to find where the atoms sit between the copper and gold in the nano alloys, which is the good catalyst for CO2 reduction, for example, here. Like you can see here, the complications of the experimental scale is around 5 to 10 nanometer cluster size, right? If we have efficient and accurate ANN potentials for copper gold, we can help to identify what compositions and how the structure look like in this. And not only that, also in realistics, we also need to include like solutions or solvent and effects. And then how can we really help to identify the compositions or even the surface structures? So what we did, we did the simulation by use the ANN potentials with the COPOCO database. And then we construct ANN potentials and then use it in Monte Carlo simulation. And in vacuum, we found that gold like to stay on the surface, like you can see here. And also copper like to stay inside of the nanoparticles. And not only that, if we take a look and use, check the computational time, if you do the FT calculations around 147 atoms, it takes around 3 hours. But with our efficient and accurate ANN potential, it's less than 1 second for one CPU core that we have. And with 4,000 atoms, with the FT is very difficult. And with our ANN potential, we can find a composition is like a 1 minute like that. And not only that, we can also use it in MD simulation and also find many different type of the compositions in your own interest or based on your research question that you have, and also including also the kinetics like in MD simulation, like you can see here. So not only that, we can also extend our database and take a look at the more complicated at the interface between the solid and also liquid here. We also apply our models with to understand the complicated battery materials, which is also the project that we collaborate with CCCE projects. So you can see that the most important part to understand the properties of batteries is most of the time is just at the nanoparticle size or interface or even amorphous regions after battery cycling, right? So with the ANN potentials, we then construct, for example, the lithium anode that we have. You can see that on the right-hand side that we have a very good agreement with our ANN predictions with the experimental voltage profile. And on the left-hand side, we could also get a lot of the compositions during the battery cyclings with efficient and accurate ANN potential. We can find all of the compositions of the lithium insertion or in extractions in the composition here. And I only show the FT results here because ANN potentials predict as accurate as the FT. And we can also use ANN potentials to predict and to find how accurate for the diffusion part. So I only select 2 compositions here from the previous slide that I see. So you can see that our ANN also predict as accurate activation energies like the FT, and also good agreement with all long MD trajectories. And then we also simulate many different types of structures, nanoparticles, and also amorphous structures. And then once we can do efficient and also accurate MD simulation, we can then also estimate the lithium diffusivity in many different compositions like you can see here. And we can also estimate or compare our simulation with experimental measurements, which should also very good agreement with experimental measurements. Yeah, there are so many different examples, but I guess that you can really try to use the ANN models, but it's really depending on the reference data. So what I feel that the lack of the lack of the FT or good database, this is also one thing that communities should also be discussed. I will just briefly move a little bit to many different types of the example that I have, but I just wanted to point it out that the most important part is that we are facing is now to generate quantum or the DFT reference database, and also the full potential energy surface or the configurations that we will use it as a reference data. So really a lot of possibilities and the compositions that we try to construct. And also there are so many different type or many different chemical species. And we always need to validate and also try to compare our ANN predictions with experimental measurements, which is from my experience, it is still very challenging. So yeah, and also really very complicated system with the solid liquid, or even with the solid interface, like we are working on here, still on the ongoing projects. We also need many different type of technique or tools to help and to work with us. Yeah, I think I will skip this part to take a look at the molecular system, but I would like to come to the summary that I hope that I could demonstrate that training machine learning models on the data from simulation is useful for accelerating computational material discoveries. And also it is important that to validate the predictions of your machine learning models. For example, compare with a more accurate first principle methods, and always compare or validate your prediction with the data from experimental measurements. And actually, machine learning in material science now is really growing really very fast. I think to support the communities and also to work out together, sharing the tools and also database, it will be really useful for the scientific communities. But some point that I want to list as from my own experience myself, I think even though we have machine learning model that we have already, but most of the time we also lack of at least a few points here that I list. So lack of the uniform from experimental data, maybe the automation will help with this. And also sometimes also lack of the standard of the exchange of models and also data. And myself, I also collaborate with the partners, for example, industry and also academics. And sometimes how to give credits and also how we really exchange, for example, the IP, right? And also need a better advanced methods. For example, the combinations of data from experimental and also computation. So this is my team that we are developing machine learning models to understand energy materials from Utrecht University, and also thanks for the experimental collaborators from materials chemistry group and catalysis. And of course, also the support from the company like a Bayer. And thank you very much for your kind attention.
Thank you so much for this very nice talk. Do we have questions?
Thank you for the very interesting talk. My question is regarding your formalism. So when you use any neural network, inherently due to the chain rule, you get the derivatives, right? You can get forces from there directly. So, but when you use Taylor expansion method, there's an order error in Taylor expansion. So why not use that chain rule getting forces compared to this one? What's your thought on that?
So you are saying like, why don't we use the direct forces from the FT directly?
No, so like you can take each atom, like you're taking the EI, sum of EI, right? So these energies, and you can get a derivative with respect to the RIJs, atoms distances.
Okay.
In like any neural network library like TensorFlow or PyTorch, anything like that. It's very easy to implement.
Yeah.
So why not use that than Taylor expansion? Maybe it can be done.
Yeah, actually we have and we use it also, but it is not very accurate, not very stable because of the forces. No.
That's the way that he was saying is the way to train the network, not with the Taylor expansion.
I mean, like, but then how the how I know that as you can. Yeah, I agree with you. But from my experience that when we work on the all complicated condensed matter, it's really take a lot of CPU time. Yeah, I mean, as I already mentioned, that if it's feasible, I think use direct force training is more accurate, like I also show here, right?
Okay, any other questions? Do we have one from Zoom? Ah, you want. Oh, you can click on Q&A.
Would you just read the question? I think I can answer.
Okay.
I will answer Q&A by typing here when I so everybody can see it later, right?
No, everybody, just read the question.
You can read the question.
Yeah, read the question. And then
Okay. Okay, the first question is from David Vanderbilt. He asked, are there classes of materials that are challenging to describe using ANN? For example, mixed valence compounds. Can you treat magnetism? I think your talk, you also mentioned this one, right? You want to give?
Well, I think that if you have a good microscopic model, you can fit the potential energy surface that reproduces that microscopic model. But if you have a mixed valence compound, the problem, I think, is with the DFT approximation, and which typically would not be good enough. So perhaps one can use some DFT plus U or some other scheme, but that I think is a basic issues that, I mean, the neural network fit essentially everything, but it doesn't provide new physics if the model that you use as reference didn't work. The neural network would not work either. So that's my answer.
Actually, the projects that we work with the Columbia Battery Center, we have also programmed the complex system that, for example, we have the lithium anode. This is a solid, right? With like a liquid, like a ethylene carbonate. This is mixed for sure liquid and also solids. And this is really very hard to train in potentials. And what we are trying to looking at, I think we need a lot of the information like the proton transfers and a lot of like David mentioned here, like the covalence and everything. This is also very hard to treat because sometimes like the lithium anodes also use maybe different class of the accuracies of the first principle methods, but the molecular system also use different class. This is also a different. This is also the challenge that we are facing right now.
Okay. Yeah, thank you so much. We have to move on. We are running out of time. Thanks. We thank the speaker again. Let's. Okay, so we move on to the next speaker. Okay, the next speaker is Mavi Fernandez Serra from Stony Brook University, and she's going to talk about machine learning approaches to improve exchange and correlation functionals and density function theory.
Okay, great. Thank you. Thank you, the organizers, for this very exciting workshop. So I'm going to continue in the line of machine learning, but actually, I guess, adding to what was missing for the previous two talks, it has been discussed that one of the things we still need is to have more accurate DFT. And so that's where we are working on. And so what we are doing is basically looking for improved approximations to exchange and correlation functional using machine learning approaches. Okay, I want to start acknowledging the people that have really made this work. Particular, Sebastian Dick has been the student that has carried all the work that I will be presenting, and Alec Wills is also working on the last parts of the talk. So we are basically aiming to approach the exchange and correlation potential in density functional theory. We work within the Kohn-Sham DFT approximation. And we're going to see this slide several times later. For the moment, all what we need to know is that a density functional, as we know, is uniquely defined by choosing an accurate, and in principle, the ansatz, the constant ansatz is exact if we have an exact expression for the exchange and correlation energy. We can calculate the total exchange and correlation energy of the system. Now, we would like to get the exact solution. That means being on the heaven of chemical accuracy. But in reality, what we end up doing in most of our calculations for real material systems is remaining within the lower ranges of this stair ladder to the heaven of chemical accuracy. Of course, ideally, sorry for this, we, of course, would like also, and often we do in small doses using hybrid functionals and hybrid meta-GGAs, but we really don't do this by default because computationally is still extremely expensive. I do have to say that I was last week at another workshop, and there was a presentation of calculating exact exchange integrals in periodic systems with a computational cost which is almost as close, or is just a factor 2 more expensive than our current GGA calculations. So probably this is already getting obsolete. Okay, so beyond this, let me just say that besides choosing an approximation, in general, when we study a system, we would like our approximation to work for every system that we study, but in reality, that's not true. And in practice, we choose the approximation that better works for the material or specific system we study. And so in a way, what we practice is the trial and error. So does the functional really fit the data? And as many of you know here, depending on what system you are studying, you choose a family of exchange and correlation functionals, which will suit you better. And some of you might be more familiar with some of these labels for exchange and correlation functional than others. Of course, if you have to work with a new system and you don't know what to do, well, what you do is usually you go read the literature and choose whatever others are doing. So I think there are sort of, in the field of exchange and correlation functional optimization, there are two trends. Of course, in a way, even if we use data to optimize the functional, we can still aim for universality. And that's the case, for example, of an exchange and correlation functional as WB97X. This is an range-separated hybrid with meta-GGA, which is actually extremely good to describe actually all the family of systems that I showed you before. It's a data optimized functional. I guess it will belong in the family of machine learned functionals in a way that is fitted and is not used modern neural network techniques, but it was fitted to reproduce an order of 2,000 data points. And it's good, it's very good to describe a large variety of systems, but still it's not ideal if you want to study, let's say, a system like water. It works really well, but it doesn't give you the accuracy that you really need. So we started working actually in this field of functional optimization precisely because of that. We were interested in studying water. And it came out that indeed semi-empirical force fields are, as Roberto Carr has already shown, actually are better than DFT approximations to describe liquid water and the phase diagram of water. And in particular, there was one that was fitted to reproduce coupled cluster level energies that performs much better than DFT. And so we wondered, can we actually do the same, fit in a DFT functional to have such accuracy? And so I'm not going to go into the details of what we did, because this, in a way, again, it was a data optimization without using modern machine learning techniques. What we did is just optimizing an exchange enhancement factor and trying to reproduce the data obtained from water monomers and dimers and trimers computed with coupled cluster level of theory. And what we actually learned from this experience was that, so this will be a GGA functional, is that yes, we did optimize. It was very good for water, but it didn't give us enough flexibility to reproduce simultaneously two-body energies, three-body energies, and monomer energies. In a way, what we learned is that the limitations of the exchange enhancement factor, which we'll see soon, which basically depends on the ratio of the density and the density gradient, the so-called reduced density gradient, is too rigid to allow for changes in properties of the local density that one needs to accurately reproduce liquid water. It worked, but only when we complemented it with a supplemental potential energy surface for the water monomer. And so there we decided to change the way of action and go to modern machine learning techniques. So that's what I'll be talking about today. So we want to, of course, include somehow node locality in our exchange and correlation functional. And I'll be showing two very different approaches to do that. So first, I'll talk about NeuralXC, where what we are doing is using information from the density to act as our descriptors to feed into a neural network, and that then can actually provide us with an accurate exchange and correlation potential. That's path number one. Path number two is a more sort of traditional approach in which our exchange and correlation functional will be written, also expressed as a neural network, which take information about local density in the grid, taking a gradient expansion. So neither of these two approaches, as we will see, will be really non-local functionals as hybrid functionals are, or non-local van der Waals kernels are. Of course, one can also include information from these two in the optimization, as we'll see. But the main reason we actually didn't want to go beyond here is because we still want our final calculations to be efficient. So let me start with NeuralXC and tell you how's the procedure. So first of all, this is what's so-called the delta learning approach, which means that we are not going to learn a complete exchange and correlation functional or energy approximation, but we are going to supplement something that is already known to work very well with a machine learning method. So that's our delta learning approach. And the way it works is as follows. So as I say, we start from a ground base level DFT calculation with whichever your favorite exchange and correlation functional of choice, in our case, DFT. And so you obtain your density, and your density with this underlying method is going to be projected into atom-centered descriptors. These descriptors are just basically electronic descriptors, are orbital light descriptors for this density that basically is a radial function times spherical harmonics. And that is going to give us this neural network that we are going to be creating, as has been already nicely presented in the previous two talk. We need to ensure permutational symmetry and rotational and inversion symmetry breaking, conservation. And so precisely this set of descriptors allows us to achieve the rotational and reflection invariance symmetry in the same way that was shown in the previous two talks. What we do, this set of descriptors can be naturally symmetrized, symmetrizing basically this spherical harmonic orbitals. And this gives us the input to the network. So the inputs to the network, which are a set of, as well previously described, Wheeler-Parinello network. We're going to have a different network for each different species in the system. So in this case, this is just an example for water, but it will work for any system. So you have a neural network for oxygen atoms and a neural network for hydrogen atoms. So Wheeler-Parinello type neural networks that are fed with the set of symmetrized descriptors. This neural network gives us an output at local energy. And so, as you can see, the machine learned energy, or the machine learned energy as a function of the density is the input for our descriptor, is going to be the sum over all the atoms on the system of the local energies provided by these Wheeler-Parinello networks. So up to here, this looks very similar to an sort of force field type of neural network. So where's the connection to actual exchange and correlation functional? It comes here. So once we have these energies, we can obtain the potential by taking the functional derivatives of those machine learned energies, which depend on the densities. We can apply in the change rule and get the density, the derivatives of the energies with respect to changes in the density, which are given basically by the change of the energies with respect to our coefficients times the orbitals or the functions that we use to describe our energies. And so that gives us a local potential projected basically on this set of atomic descriptors, which is then added to the line potential. So the final NXE or machine learned potential is the sum of these two. Once we have this full potential, we can apply Hellman-Feynman theorem to calculate forces is also self-consistent. So the way, of course, it works, we need two separate codes. You have whichever your favorite DFT code of choice. It interfaces with this Python called NeuralXE, which projects, so it feeds the density and projects on the descriptors, creates the neural network. This all machine training loop is done outside the DFT code. You get your functional. And then we've created a library, which is called LibNXE, which is written to match libXE. Can be interfaced with any electronic structure code that is interfaced with libXE, which will provide your serialized model, your model that can be then added to your underlying potential and to run your DFT calculations. Now, something which is really important here is the fact that, of course, we need to optimize the potential, meaning that we need to minimize a loss function to reproduce the reference energies. We are fitting against very accurate coupled cluster reference energies. And so we start from a given density obtained on a set of atomic positions and with a set of reference energies. And we have what we call a baseline density. And so we optimize here, W will be the parameters of our neural networks, minimizing this loss function. But that's not really what we want to do, because the true loss function that we want is that one that gives us the optimal parameters for the network in the ground state density of the corresponding functional. So we want this to be self-consistent. So this is the so-called double optimization problem, which is difficult to solve. And the way we do this is by what we call iterative training. We start with a given raw density, and we get a optimize a set of parameters. And now that we'll get a first level exchange correlation functional. Then we add an extra layer to our network. We train the network again, and we continue until the full system is self-consistent. So I'm going to show you some results for this method. First of all, transferability. So this is all trained in the MOV data set by the Miller Group in Caltech. So here we've trained basically 50 ethane and propane samples. So, and we are testing them. So basically these are the systems that we train on. And the samples are basically different configurations and of course different energies. And we test on systems that the network was not trained for. So basically butane, so butane and isobutane system. And you here can see that the error, and these are the results for the standard exchange and correlation functionals, and these are the results for our neural XC. You see that the mean absolute error is much reduced with respect to any of the exchange correlation functionals we use here. What we see here is that there is a deviation. Here the error is very small, but there's no systematic deviation. Here there is, and the reason for that is because we train on systems which didn't have the right chemical environments for the test systems. In particular, these test systems are all double bond systems. The training sets are single bonds. And so that shows that if in your density there is not enough information to describe the correct chemical environment, then in principle, you are not going to learn from it. Even though yet the accuracy for those is still much higher than those of standard DFT functionals. So then with this functional, with this method, we took back again all the data for water and retrained an exchange and correlation functional just for pure water. And as you see here now, we obtained results here. We didn't need to take into account a potential energy surface for the monomer separately. So here what you see is that this neural XC functional optimized for water outperforms any of the other functionals that we tested, including this one, which, as I told you, is a hybrid and meta GGA based functional, and produce per correlation functions which are at the same level as experiments. So this functional, of course, is still very specific for the system that we train. Despite that, we actually also were able to show we never train on breaking bonds. We always train on fixed bond geometries, but the functional actually can't extrapolate beyond where it learned. And you can see that the energy barrier for proton transfer, which originally, remember that we start from PBE, is very badly described. Our neural XC functional matches coupled cluster level of theory, even though it was not trained for it. So that means that there is a lot of information in this density, and there are correlations in the density that the functional is being able to capture. I do want to point that there are other related methods that came after that. Deep Hartree-Fock is actually by the group of Wayne and E in Princeton is very similar. What they did is instead of learning from the density, they learned from the density matrix and also projecting on atom-centered descriptors. The functional itself, the method has been used to optimize multi-configurational approaches So basically they use Neural XC to increase the quality of multi-configurational approaches. However, there are challenges. And I think the most important one is the fact that we really not making use of all the data because we are assuming that our densities are basically, we are not making any use of the correctness of the densities. We don't use the exact densities, we only use the exact energies in our loss function. So the question is, how can we do that? How can we improve our functional, which not only corrects on energies, but also on densities? I'll skip this and go directly to this. So for that, we took a very different approach. This is XCDiff, which is a data efficient and physics-aware method to optimize empirical functionals. It's data efficient for two reasons. First, because it makes use of prior physical knowledge to optimize the neural network parameters, but also because it makes use of the exact density in the optimization. So to do that, basically, we change framework, and we are going to make use of differentiable programming. I guess many of you are not aware of this. Basically, all artificial intelligence and neural network-based libraries are written in languages which allow for automatic differentiation. That means that for every operation, they automatically, every functional operation that you perform, they automatically implement the corresponding derivative. And that actually means that if we rewrite our constant equations in these languages, you can choose your favorite one. In us in particular, we work with PyTorch. We can prove the response function of the output with respect to the input and any internal parameters of our calculation. So this opens the door to actually compute any type of response function without having to program the analytic derivatives that, as many of you know, is extremely expensive. That basically was what limited us, is that we didn't have the derivatives of the changes in the functional parameter with respect to changes in the density. That was shown as a proof of concept by the group of Kieran Burke, and that indeed they can be used constant equations as their regularizer. And so what we're going to do is basically now optimize functional in the traditional way. So we are going to replace our functional by something that looks like this. Will depend on properties of the density expressed in a Grease density, the gradient, and the kinetic energy density. So we are going to work in a meta-GGA framework. And these are going to be the parameters that we're going to take as an input. And of course, our final functional will also depend on the parameters of the neural network. So of course, if we write this outside loop, counterclockwise loop, represent our self-consistent cycle, and if we have implemented this self-consistent cycle on a fully differentiable programmable way, it means that we can invert this cycle, go backwards in all these graph, computational graph operation, and obtain the gradients with respect to every single operation in that graph. So it's easier to see it in here. We start with an initial density, and remember the problem that I told you before about the double optimization problem. We actually want to optimize the parameters in the converged density, not in the fixed density. So we start with a fixed density, which is provided by a given initial exchange and correlation functional. It doesn't matter what you start with. This is not a delta learning. This is a full functional learning. And what we are going to minimize is a loss function that has two components. One is the energy as before, and one is the density. So we want both energies and densities to match the references. But not only that, we want to optimize that in the full convergent self-consistent cycle, which means that we are going to need to obtain the gradients at every part of our iteration. So this loss function, the energy is the sum of these energies at each self-consistent cycle. Now, I said that it's not only that, we also want to implement constraints. So these are our input parameters, density, this is a spin polarization, this is the reduced density gradient, and this is the kinetic energy. The first thing that we'll do is, of course, they'll span very different orders of magnitudes. So we'll apply a transformation that will bring us to a small unitary range of values for all our parameters, and all the parameters expand the same order of magnitude. In addition to that, already this constraint in here imposes a soft condition for the derivative of the exchange enhancement factor at S equals 0. And the next thing that we are going to do is we are going to optimize separately an exchange part and a correlation part of the functional. So we'll have two separate exchange enhancement factor and correlation enhancement factor. In order to input constraints, in particular the spin scaling and the uniform density scaling, what we do is we drop the variables 0 and 2 from the exchange part, meaning that again, the exchange factor only depends on the reduced density gradient and of course on the kinetic energy part, and all the uncorrelated density and gradient changes are accounted for in the correlation enhancement factor. What you see here in color, green imposes the homogeneous electron gas limit by taking this additional transformation, which ensures that the value of the two exchange factor is correct for S equal to 0 and X3 equal to 1. And finally, we make use of the form, this functional form, to impose the local Lieb Oxford bound and also the non-negativity. So the local Lieb Oxford bound is included, making a 1.174 that ensures the Lieb Oxford bound, and the non-negativity of the correlation energy is by making A equal to 2. So with that, we are actually naturally imposing constraints which are very necessary to have a well physically and transferable functional. We train with actually a very small number of systems, as you see here, 21 atomization energies and densities. So the densities are coming basically from atomic structures, ionization potentials, and barrier heights, and then total atomic energies. And with this, we test on a very large system database, the MTK55, which basically measures many different properties, barrier heights, reaction energies, non-covalent interactions, intramolecular and intermolecular, and reaction energy barriers. And I'll show you the results. And comparing, basically, remember we are remaining in a meta-GGA approximation. What you see here are errors for energy. Greens are GGAs, blues are meta-GGA, and oranges are hybrid. This is our functional and performs better than the best of the meta-GGAs, which is SCAN. That's for the energy. If you actually, it's interesting that we only use 25 data points, and the Minnesota functionals, the GGA functionals, use a much larger number of data points, and yet they perform in average worse than this functional. When you look at the densities, so these are the errors on the densities, they are, as you know, the errors on the densities are in a way all over the place for all the family of functionals. That's what's found in the reference that I pointed out before. In general, non-semi-empirical functionals perform much better for the densities than semi-empirical functionals. And as you can see in here in particular, the ones with the smaller functionals, B97 has in GGA has the smaller error on density. This is where we are, improve everything, even some of the hybrids. So that inclusion of the density makes things much better. What we did in here, I want to show, is that we can plot I mean, remember these are errors on energies and densities, which are different magnitudes. So in principle, we cannot compare one with each other. But if you plot them in the same, so here is the error in energy, here is the error in density, and you plot all the functionals that I was showing you before, what you see is that there is a clear separation between hybrids. So this is where you want to be, a small error both in energy and density, and in between meta GGAs and GGAs. But even more, what is really interesting is that there is a very strong linear correlation between energy and density error for non-empirical functionals. As I told you, non-empirical functionals tend to have a much better description of the density. And so we can take this linear correlation to define a combined metric for energy and density, and then measure it against all the functionals again. And so this is our combined metric, which combines the difference between the energy. Basically, what it does, it converts a density error into an energy error by using this linear scaling relationship. And there, what you can see is that the functional that we optimized still is the better among the GGAs, and is probably at the level of the meta GGAs. I do have to say something, which is, I mean, our aim, of course, was to test whether these methods work. They do work. They certainly improve. The improvement is not outstanding. I'm done. Scan improves over scan, but not by a large amount. The DeepMind, the Google team, basically after us, proposed an alternative optimization. In their case, they use a local range separated hybrid, which works much better because it's a local range separated hybrid. So I'm gonna leave it here with conclusions. I think these methods are actually bringing the improving of the exchange of density functional theory quite far away. I think in very few years, we are already where we've been, we were, what I would say human intelligence have achieved in 50 years. And I think there is still a lot of improvement, and the search for the so-called universal functionals might not be that far away. With that, I will thank you for your attention.
Thank you for this very nice talk. So do we have questions?
So I'm trying to understand your formalism. When we talk density, it's a field quantity, right? It's not a one single point. It's not Rij. So how, when you take a density, do you take a cutoff to represent your density for each atom?
So you're talking about the first.
The first one, yeah.
Yes, there is. As you see, this it is. And we go in here. I mean, it's not clearly seen, but basically it's a product of spherical harmonic times radial orbitals, and they have finite support, meaning they are strictly zero beyond a given radius. So
what is it, like Wigner's size radius or something like that, or?
No, it basically is very similar to the radius that are used in standard numerical atomic orbitals.
Oh, I see. It's like 1 year. I mean, got it. Okay.
Yeah.
And one more question was,
Sure.
I'm blanking out. Solids. I am okay. This can work for molecules, but for solids, you have to satisfy periodic boundary condition.
Mhm.
I don't see this formalism can do that, right?
Yes, absolutely, indeed. Okay, so these calculations, these are all periodic. So I hear this is all with periodic boundary conditions. This is liquid water. It's not a solid. We did also ice and so on and so forth. But this is perfectly amenable for periodic boundary conditions. Indeed, all you need is to have your density in your simulation cell, whether the density is on a periodic cell or on a non-periodic cell, it doesn't matter. So the projection that is done taking periodic boundary conditions into account.
Very
Yes.
exciting. Thank you.
Okay, we have time for another question. Is there another one in the audience? Yeah, all the way in the back.
It's a beautiful idea to go back to the original idea of functionals of the density. But it seems to me that thinking of hybrid functionals as really functional of the density, because the wave function of the density puts in physics That's just simply not in the other approaches that try to just stick with the density and you band gaps, things like that. So can you say more along that line of things more than just structure?
Yeah, so yeah, that's a great question. And indeed, as you've pointed out, the hybrid functionals are functions of the wave function itself, so indeed include information of the exact Slater determinant. Yet, you can still, I will argue that all the information is still on the density. The question is how to go beyond no local effects. And that was shown in the DeepMind team. That's precisely what they did. They optimized a hybrid functional, and let me just very quickly just say. So what they include is the local exchange energy density, which is something that usually is not computed, and we usually use the total energy density, not the local energy density in the grid for the exchange part. But once they include that, they can show that indeed the band gaps improve very much. I think there's two reasons for that. First, including the exact energy density in the grid, but also the way they do the fitting is they also impose fractional charge constraints, which are what are really necessary for this type of optimization. And I do want to say that using those fractional charge constraints that we are working on now, we can start seeing that even just having local density information, including fractional charge constraints, already gives you improvement on the band gaps. So I will say that if one wants to go beyond there, you can still do it on the density, but you need to find more non-local descriptors for that density.
Right, and those are highly connected to band gaps.
Yes, correct.
Very good.
Okay, we are at the end of the, we are running out of time at the end of the session. So let's thank the speaker, Navi, and also all the speakers of the session. And we're having a break now, and we will reconvene at 11:15. Yeah, exactly. Okay, everyone, we are going to continue. Okay, everybody, welcome to the second session of this morning. And yeah, the second session is a mixed session. The first speaker is Talat Rahman. She's from University of Central Florida, and she's going to talk about correlated materials, and in particular ab initio tools for uncovering ultra-fast responses of functional correlated electron materials. So please take it away.
Thank you so much. Thanks, Jonathan. And thank you so much to the organizers for inviting me. When Renata got in touch with me, I said, yeah, I wouldn't want to miss this at any cost. I'm very glad to be here to see some old friends and make new friends. And so this is just really a pleasure. She also wanted me to talk about what we have done with dynamical mean field theory. And I will talk about that because this is about recent advances in electronic structure. But I did want to give you a little bit of flavor for what we do. But before that, congratulations to Richard, not only for turning 80. It's nice to see, you know, he's still very active and hopefully will continue for many more years. And I was just reminding him of the first time when I met him, which was long, long ago. So that tells you how far back we go. And I'm also very, very excited to see how the US-Africa initiative has taken. So that's something that, again, I'd like to know more about and be more involved in. Some of you may be wondering, where is University of Central Florida? Particularly since it is called UCF. And so the first time when I introduced myself to someone, they said, oh, is this University of California in Florida? So it's not. It's actually a relatively new university, but it's an amazing one because it has this many students. So it's the largest university in the country and a very diverse one. So that also is another reason why I'm very interested in collaborations outside the US, because we do have a microcosm of the population in the state. And we are a minority serving institution. We have a large number of Hispanic students, but we also have a very large number of African-American students. In particular, we have a bridge program in physics with which we have increased the number of students from underrepresented minority groups to, which was something like 2 to 3% in 2014, and we have about 20% right now. So we're very proud of that. And that is something that we are trying to promote because that's the way to go. So, and because you are from so many different perspectives and interested in collaborations, I thought I'll mention a little bit about what we do. And this, I think the talks will all be available. So the majority of the work, actually more than 50% of the work I do is in chemistry. It's more in understanding reaction mechanisms and molecules on surfaces and so on, which interestingly enough, because you can have magnetic molecules on surfaces, spin crossover molecules, molecular magnets, and so on. And they are right now being used or being touted that they may be suitable for quantum computing and so forth. So there's a good bit of work going on there. But you know, when we look at all of these things, what you realize that when you're talking about functionalities of these materials, that a lot of times we do get stuck. We get stuck in two ways. And the earlier speakers today, all of them, all three of them, showed you how you could use machine learning and other techniques, which when coupled with DFT can allow you to go to realistic systems. Because if you just rely on DFT, then there are a number of issues. In particular, I think one of the things we forget is that we have to take into account the fact that we live in a world which has temperature and lattice vibrate. And so molecular dynamics is the way to go, but then it has to be supplemented with potentials that are really valid. So that is really the way to go. the next question that comes in is that, are we describing all interactions properly? And so the talk that I will give here right now will focus more on what about systems in which electron correlations play a role, and that cannot be then done with the DFT. So, so before I go on, I wanted to thank a good number of my colleagues here. And I particularly wanted to bring to your attention my colleague from chemistry. His name is Feng Tao. Some of you may have heard about him. He's right now fighting for his freedom. He's basically been arrested and he's under this China initiative. And they even had a hearing and he's fighting it, and hopefully he'll win it, because I know very well the case, and it's like the other cases that you know about. But he's still very active. So he's home with under surveillance, but he's active and he's writing away. And what we're working on with him is looking at single atom catalysts, and he's writing review articles and books and so on. Okay, so what about this? Why get interested, or why even try to look at these systems? So one of the things is that vanadium dioxide, this is something that those of you who have been in the field know that this has been there for over 50 years. This was the example of transition that it undergoes. In fact, Renata has a paper from long back on it, and very nice paper on MD simulations in this ab initio MD simulations. So what is new about vanadium dioxide? Well, the point about vanadium dioxide is that it undergoes both a structural and a phase change. So it goes from being an insulator at lower temperatures to a metal at higher temperatures, and it undergoes also a phase structural transformation. And both of them seem to be connected. In fact, if you look at it experimentally, they find a number of phases, and that has made basically identifying every aspect of it difficult. What was interesting is that when they did these measurements, so there are two measurements that I'll show. This is femtosecond photoelectron spectroscopy. And this one did not show it that clearly, but the next experiment did. So essentially what they found here is that so you're looking at the decay, you're looking at the intensity, how you excite the system, and you're looking at the way that the intensity decays. And this is the usual. So this is the one that happens at the picosecond time scale. But then there are two others that they find distributions. So system is excited, it is going to the ground state, and there are two other decay that happens, and they happen at the femtosecond time scale. So what is causing that? This one is clear. If you're at the picosecond, then of course phonons have to be involved. All kinds of interactions need to be taken into account. But these were what were intriguing for us. The other one, which is beautiful experiments. I mean, the first one is beautiful too, but these were taken in 2014, and there's some repeat experiments done. This is the group in Canada. And what they do is that they actually look at the metallization. So you're seeing this metallization that is going on, and metallization actually proceeds. It's actually spatially also, they see how it progresses. But more than that, when they sit on, they're looking at the diffraction intensities and look at the different beams, and they see that some of them undergo a fast decay and others go a slow decay. So they or decay or rise, for example. So rise in intensity. So this is just looking at the intensities of the different beams, right? So basically over here, so this is the one that really is the one that we're thinking about, is the one that is there as you excite the system, and then it goes down. So their analysis, which we find convincing, is that initially the system, when you bring light in, not temperature, when you bring light in, the system basically undergoes a transition from being an insulator to a metal. And then the rest kicks in. And then, of course, it's both the insulator to metal transition as well as the structural transition. Okay, so what is interesting about this, and this is where then DMFT comes in, because essentially what DMFT was able to do, not in the ultra-fast region, but just in terms of the transition, that essentially the way you get the density of states at the Fermi level, near the Fermi level, that is what basically then determines whether it's going to go through the transition or not, okay? So these were some very interesting experiments for VO2, for which there was no ab initio explanation, okay? And then the other one, which we found even more fascinating, was this metal nickel, which we all know very well. And nickel is not one that is supposed to be strongly correlated. It's a rather benign metal most of the time, unless you think about nickel oxide, right? Nickel oxide has been a perennial problem when you come to defining nickel oxide. Nickel oxide is a very strongly correlated material. Most oxides are, but just nickel itself, and this is again, Borapé in Strasbourg did these beautiful experiments. And this they found that there's this large demagnetization. And since then, this has been done over many labs. And basically, the conclusion is that this demagnetization is happening within 50 picoseconds. So you can see, if you're thinking about technological applications, how good it is, right? It undergoes about 60% decrease in magnetization within a few femtoseconds. And so it can be a very fast switch for various purposes. So this one, and I would like to give credit to, I think it is published, yeah, to 2019. So this is a work by Lin Wang Van at Berkeley, who basically did a very, he kind of summarized the 20 years of data, of theoretical work that has been done, a lot of TDDFT, because we're looking at time-dependent response, right? A lot of TDDFT work, which was not able to reproduce this demagnetization. So he built different models and came up with all kinds of ideas, and finally came to the conclusion that he can get this if he has a parameter that controls electron-electron interaction. Furthermore, if there is disorder in the system. So again, not ab initio, but a beautiful piece of work. Okay, so what are we going to do? So, and I know I'll have to move fast. So essentially then, what is missing? So what is missing is, how do you describe the excitation of the system, the excited state charge dynamics, right? That's what we're talking about. And that's not the forte of DFT. So we need to go to something that goes beyond. And what I'm going to argue over here is that while the DMFT is really good, it is pretty expensive computationally. So what we have done is basically use DMFT. So in a nutshell, what I'll show is that we use DMFT to calculate the electron susceptibility, which then we use to be the functional in TDDFT, and then TDDFT becomes a much more manageable program to solve, okay? All right, so so that's the goal, that we want to do that. What we are really looking for is, and again, this is where we can learn from Marivi, who gave the talk before me, is that if we can find a way, because now, we've done this for a good number of systems, but if we can bring machine learning into it and try to come up with functionals which could have some kind of a universal form, and that would be really, really good. We have one for nickel, but we would like to build one that's universal. Okay, so again, TDDFT, what you know, if you're familiar with it, and if you're not familiar with it, it doesn't matter, because it basically says that just like we have the Kohn-Sham equation where you have the orbitals, which and you can describe the ground state, what this basically says that if you have this, you're looking at the time-dependent behavior of the system, then as long as we know the density of states, again, the same thing as DFT, one variable, like one observable, the density of states as a function of time and of course space, then we know everything. So what happens there? What basically, what I want to come to here is that essentially it is this is the potential, right? So this potential is if you think about it, this is the external potential, right? Could be the ionic part, could be the external potential that you apply, or both. And this is the Hartree term, and then this is the exchange correlation term, okay? So basically these two are fixed, right? So this is the one that we can play with, and the hope is that we'll get one that reasonably represents the system. So how do we do it? Well, first of all, you apply linear response theory, right? So basically, I mean, this is not to go through details, But let me just emphasize, and again, I'll give you a reference in one of the slides because my coworker Vladimir Turkowski just wrote a book on DMFT and used all of the methodology that I'm showing you here. But essentially, in principle, what you can see is that that's the change in the charge density, right, as a function of the external probe, and that change is then related through this functional here. That's your exchange correlation functional, which again is formally defined by here, right? And of course, then what you could use some adiabatic approximation. I'll show you how that doesn't work in a lot of cases, but you can get rather trivial forms for this, but in principle, you know where it's coming from, okay? The main thing, which again, I will not show you all the algebra here, is that this functional, which when written in a frequency dependent form, can actually be written as in terms of the DFT. So this is the susceptibility that you would get from DFT. And this one is the susceptibility that you would get from TD-DFT. And this is, of course, coming from the Hartree term, okay? So essentially, this is going to be the linkage, right? So again, what our interest here is to find this. And for this, we are going to rely on DMFT, all right? Okay, so the simple one, which you are familiar with, is just the adiabatic local density approximation, and there, if it is function of only one time, and if that is the case, so what we find with this, and I'll show you examples of how it doesn't work in the cases that we are interested in. Okay, all right. So this goes too fast. Okay, yeah. Maybe. So again, this is just an introductory slide, because how do you bring in these materials which have localized orbitals, DNF orbital, right? So if you have localized orbitals, then you have this term, this hopping term, right? So the electron wants to hop from one orbit to the other. So it costs a certain amount of energy for it to hop or gain certain amount of energy as it hops. That's one term. That's the kinetic energy term. And of course, if it goes to a site, if it is already occupied, it's going to have a Coulomb repulsion, right? So it's a Coulomb repulsion term. And of course, because of the fact that, it's going to have repulsion, it depends on the spin. So Pauli's exclusion principle is also taken into account. So that's essentially what we're doing. Of course, it's easier said than done. So essentially, that's what we're talking about, that it doesn't, if it has to be two electrons have to be in one site, they have to have opposite spins, right? So basically, that's essentially what we're talking about. And what we do is that in principle, you solve a much larger a Hamiltonian, right? You do it because you can't get away with doing the single band model that a lot of people have done. So you look at multi orbitals. So, the 5D orbitals, for example, then of course you'll have F electrons, you'll have the F orbitals and so forth. So the more orbitals you had, the more complex the problem becomes, right? But the main ingredient in all of this is essentially what you're trying to do is to get the Green's function. And once you get the Green's function, then of course, you can calculate the electron susceptibility, right? And in order to calculate the Green's function, the culprit is this thing here, which is basically the self-energy. So the whole focus then goes in as to what you do to calculate the self-energy for the system and how reliable it is and so on. And this is where I said, I'm not going to go through this slide at all, except to advertise that this is a book that was written by my colleague Vladimir Turkowski, with whom I've done all the work that has been related to DMFT and also TD-DFT. Okay, so lots of algebra, lots and lots of algebra. And, but he's very patient. And so he sits with students and they go through all the algebra, and hopefully no mistakes like Richard, you found in Alex Maradudin's calculations, but it's a lot of algebra. So anyway, what happens here is that you're using the Hubbard model, and so what's different from DFT? Well, what is different in DMFT is this peak that you see, right? In the specular direction. And of course, all of it depends also on what U is. So again, this question I'm sure will come up because you've got DFT plus U, and then you've got DMFT. In DFT plus U, you have DU as an explicit parameter. Of course, you can calculate it from first principles, but usually one makes educated guesses and so on. What is the difference between DMFT and DFT plus U? DMFT also has U, as you saw in the equation that I had before, right? So U is a parameter. It's just that the dependence of the results on U is not so strong. And furthermore, if you compare DMFT to DFT plus U results, what you find is that it shows up in the orbitals that are in the at the Fermi level, their occupancies are different. And for most of the cases that we've been comparing, DMFT has given better results, but there are also approximations in DMFT. So this is not like everything is exact. So that's exactly what happens. And this is the famous paper by Kotliar and others, where they were able to show that you get this central peak that was missing in all DFT calculations. All right. So let me then bring you back. This is the slide I talked about before. And so this is what we are after, right? So this is the same slide, that what we are after are these susceptibilities. So how do we go about doing it? And again, what we're going to do here is that we are now going to look at this thing here. So now you're looking at the TDDFT, and in TDDFT, there is this exchange correlation functional, right? And now what we're going to do is we're going to use this one to give you the exchange correlation function. So I think what I have done is there were several slides that I've taken out of here because my time is probably limited to another 10 minutes. 10 minutes, okay. So basically then what I want to do is, so you can refer to the papers and others to see how we do it, but this is exactly how it is done, all right? So what do we get? So let me go to the experiments that I mentioned. And these are these papers. I think the first one is in Science. And again, I can provide you with references. But and what they see over here, so the blue ones are the slow decay ones, the red ones are the fast decay ones. And so that's exactly how they're monitoring how the structure is changing. And this is all being done at the femtosecond level, okay? And what they're measuring also is the conductivity. So it's the conductivity of the system that they're measuring, because if they are, before shining the light, the system was an insulator, albeit the band gap is only 0.66 eV. Okay, so that's what they're seeing over there. So again, this I've already summarized. So basically the thing is, so what was the problem with it? So if I just go back and just summarize about what was known about equilibrium. So in equilibrium cases, again, it was not until they came up with this DMFT that they were able to show that there is a band gap, and that is what causes, and that you go from one structure to the other, and how with the structural change, the orbitals change to provide you with the kind of phase transitions that you need. So this is what I've already mentioned, and the point to remember. And the reason I'm even talking about it, because I would have had to include phonons in the system if they didn't have these results at very low very fast time scales. And what our assumption, and this is now kind of confirmed by diffraction experiments, that indeed at the very short time scale, the structure has not changed. So we do not have to worry about phonons in that short time scale. Of course, if you want to explain the whole thing, you have to bring in phonons. Okay, so what happened here? Okay, I'll skip that. So essentially, this is what I just summarized here. Basically, it's opening up this gap that was important. And you know where they are coming from. They're coming from the d orbitals of vanadium, and they're coming from the oxygen p orbitals. All right. Okay. So then what happens? Okay. So this is what we found really to be very interesting. If you remember, this is the curve that I had shown you. And what we find, these points are coming from our calculations. So essentially, what we are getting is that, if you include, and so, what we are getting is that how did this come about? And I'll show you that in a second. So essentially, because that exchange correlation functional has a memory term in it, has a time-dependent term in it, okay, frequency dependent. So essentially what it is saying is that the electron-electron interaction is time-dependent, which is to be expected, right? Because electron is going to hop from one orbital to the other. And if it's going to go to an orbital where there's already an electron at a particular time, it's going to have a different, a different interaction than if there were no electron in there, right? So that is time-dependent. And basically that memory is kept in mind. And if we do that, then we get what they observed. So let's say, so basically then that was that. And then what we are showing over here, which was quite interesting, this is not a direct comparison, but here is what we're showing you. Here we're looking at the chemical potential of the electrons and the holes. So again, you excite the system, you create these whole electrons in the excited states, you've left holes in the valence band, and then you follow their time evolution as a function of time, all right, using that time-dependent exchange correlation functional. And if you do that, what we find here is, again, the holes and the electrons, they both go back to their potential there, and they do that. So the main thing to point out here is that it is of the order of hundreds of femtoseconds, which is kind of what they saw over here. So that's what we're making a kind of a qualitative agreement. And this thing here, so essentially, what this is also saying, what are these lines, is what we would get if we had the adiabatic approximation. Okay, so essentially, not only you have electron correlations, but also what we are saying non-adiabaticity, which I would basically prefer to call memory or a time-dependent, frequency-dependent exchange correlation functional. Once you have that, then that gives a better agreement. This one would have shown that it would have equilibrated much earlier. Okay, so there are more things which I will not have time to talk about because I do want to tell you about nickel. But essentially what it shows here, and the case that we're trying to make, is why is the time dependence important? And essentially what we find is that there is a much slower decay and this formation of the metallic zone. So essentially they're shining light and they're looking at how the metallic zone evolves in time, that we would say that these effects are worth taking into account. Okay, so I think I'm going to skip this because I want to go over, if I can, to this other problem. Which I mentioned to you here. And how does this happen? This was harder to explain because in the case of VO2, we could explain everything on the basis of excited state charge dynamics. In this case, we have to look into spin dynamics because there's of course demagnetization that is happening. Okay, so what really causes this interaction? And remember, in the paper and in the literature for the past 20 years or so, what they've been talking about is basically maybe it is spin-orbit coupling, but spin-orbit coupling does not allow that much of a decay, maybe about 5% to 10%. If you use LDA or any other kernel or exchange correlation functionals, the decay is of the order of 6% and not 60% or 40% or something that has been observed. Okay, now in a more recent paper, they actually did match the experimental one, but then they had to use the fluence that they used was about 100 times that in experiments. So, there was a problem with that, but it's been an ongoing quest for that. Why does this go so far? I'm going to skip this because you do basically what you do, except to say that essentially you set up your DFT calculations, then you use the Kohn-Sham orbitals from DFT to put it into DMFT, and you have now reliable codes that are available. Abnet has, other people have, we have, which is not yet user-friendly, but should be soon. So those things can be done. And then once you do DMFT, you get the susceptibility, and then you go into the other. So, gosh. So what is different? So subtle differences. We didn't expect this to be very different, but if you look at the DMFT results, and these are the different orbitals, and then you see just the occupancies are different, right? So if and basically if you look at the Fermi level, right? So that's what's interesting about it, is that there is a subtle decrease in the occupancy of the up spins and increase in occupancy of the down spins. Very subtle effect. I think one of these days I'll learn how to use this. Okay, so again, very subtle here. We are again now looking at the imaginary part of susceptibility and looking for just little things that are different, right? This is your DFT, this is DMFT. When you go in there, slight kink over there, okay? And this is what I wanted to show you. So basically, this is your exchange correlation kernel. And essentially what you see is that, and this whole thing sort of dies down. So it's only in the first few femtoseconds that you see these oscillations, which are actually responsible for everything that we are seeing over here. Okay, so how do we compare? So these are the results. So again, experimental results showed about 57%. What we have got is about 34%. And if we was for the same parameters in all of this, that was the result that people were getting. So it's a factor of 10. Okay, all right, okay. So I think I have to wrap this up very quickly. And of course, it will wrap very quickly if I don't know how to advance the slides. One more. All right. Okay. So essentially, this is a curve that I wanted to focus on for a second. And essentially, what you see is that these are your up spin down electrons there. And those are the ones that are really taking major part in it. And I think I should probably bring it to the last slide, which basically says that, what we have seen is by combining these two methods, we have found a way in which we can look at the response, ultra-fast response of some of these systems, which have been intriguing researchers in the field for a long time. And thank you very much for your attention.
Thank you, Charlotte, for this very nice talk. Do we have questions from the audience? Alex.
Thank you for the nice talk. So basically, can you elaborate briefly on how
I think your thing is not on.
I think it's okay. Okay. So can you maybe briefly elaborate on how you construct the exchange correlation kernel for the TDDFT? I mean, you mentioned briefly that you constructed by measuring susceptibilities in the DMFT solver.
Right. So essentially, what you do is that you go to DMFT. You're looking at the self energy. You calculate the self energy in DMFT using, it's like an Anderson impurity model that you use to get the self energy. And there are various approximations because essentially it's an impurity in the field of all the other electrons, right? So that's what you use. Once you've got the Green's function, then you calculate the electron susceptibility. That is then connected. There's a direct relationship between that and the exchange correlation kernel. So,
okay.
So then the TDDFT is just standard TDDFT, except that the exchange correlation functional has these interesting oscillations in it that it doesn't have if you didn't take these things into account.
Okay, thank you. I mean, maybe we can also check.
Oh yeah, we can talk later about that, yeah.
Hi, just very quickly. So I remember from Hardy's talks about the magnetization, they had to include those extra exchange correlation B fields and all of these other things. So, and they did it at the adiabatic level. So did you include those in your calculations, and or would it be possible to extend it towards that? And they seem to be crucial for the description of the magnetization.
Okay, it's for the dispersion.
I'm sorry?
They seem to be crucial for what?
For the description of the demagnetization and for the in TDDFT. I mean, that's what I remember from his talks and Sangeeta's talks.
And okay, so no, the answer is, so the question to ask is, how do we get the spin flip interaction? So I mean, that's the main thing, right?
Right. Well, they were showing that in order to describe something with spin dependence, you have to include actually in your FXC kernel also exchange correlation B fields that are generated by the currents. So essentially, you need to expand your TD-DFT equations.
I see. So in effect, I think what we're doing is similar, because we're using this non-collinear model, and that is what is introducing that interaction. So in effect, it is similar. Yeah. Thanks.
So we have time for one more quick question. If there's any other question. If not, then yeah, let's thank the speaker again. Why the pointer? Oh, here it is.
Sure.
Thanks. Oh. Okay, then let's move on to the next speaker. The next speaker is Yang Sun from Iowa State University, and he's going to talk about simulations of iron in the Earth core conditions.
Thank you. So, can you hear me? Okay. So today I'm going to talk about some simulations of iron on the Earth's core conditions. So clearly from the title, you can see it's a bit different because it's kind of on the background of the geoscience. So, but still we will see that how useful the DFT and molecular dynamic simulation can bring us knowledge of these really deep interior conditions. So first, I would like to acknowledge my co-workers and collaborators, especially Professor Renata Wojtkowicz, who bring me into this exciting field of the geophysics and really show me how the DFT could be used in this area. And also, I would like to acknowledge my co-workers at Iowa State University and AMS laboratory at US DOE, and also Michael Mendeleev, who is at the AMS Research Center at NASA, and also some experimental collaborators at UT Austin and people at UHP STAR at Beijing, and also the funding agency National Science Foundation. So today I'm going to mainly focus on two topics. One is the two-step nucleation of iron under the Earth in the core conditions. And also another is the discovery of iron-rich oxides with really new compounds at the core pressures. So here is a background of why we are so care about iron. So it has been well known that Earth has this layered structure, and the core constitutes its major part, which is almost 1/3 of the Earth's mass. So present core mainly contains two parts, liquid outer core and solid inner core. And its iron is the dominant element with like 5 to 10 weight% light elements in it. And the solid core is, so the outer core is mainly the iron melts, and while the inner core is mainly the solid iron. So it's generally believed it's to be the HCP iron, while the BCC iron was also suggested. So core has been a central part of the Earth because this inner core is continuing growth, which actually releases the latent heat, and is the major power source to drive the current geodynamo. But how the inner core is formed and what is the age of the inner core? This is actually not well answered. So from the geophysics models that the liquid core was formed around 4 billion years ago when the Earth was first formed. And during this core mantle differentiation, you have the dense iron settle into the center, while the lighter elements form this mantle. So this time scale is around 1 billion years. And the question is how this solid inner core was formed. So currently there is two ways to estimate the age of the inner core. So one is the thermodynamic modeling of the cooling process of the Earth. So the key idea is that you have this heat convection in the inner core, in the liquid core, and then you also have the heat flux at the surface. So the key quantity to measure this age is to measure the iron heat conductivity at the core mantle boundary conditions. So with this, but this quantity is really hard to measure. That is why you can see from this table with this thermodynamic method, due to different iron heat conductivity, one can get very different results here. So I think the most close recent results is from experiments and DMFT calculations. And another way is really a geology method, which is to look at the how the Earth's magnetic field was changed. And this record was obtained from the rocks, so which is so-called the paramagnetic record. But at this stage, there is no consensus has been reached for either T method or P method, and the range is from 0.5 billion year to 2 billion years. But what is more important is how the liquid core was formed. But this was not well considered, but actually could provide our ideas that if you know when how the liquid core was nucleated, then you will probably know how it was when it was formed, right? So there is some conditions for the liquid core by the time the solid core forms. First is that it has been well equilibrated for almost 2 billion years, and also the core mantle boundary is very stable, which inhibits the transportation of materials. So therefore, the solid core are most likely formed via the nucleation process. So here I bring a little bit background of this nucleation, which I call to Dr. Carr's nice work on the water nucleation. But this also happens in the deep earth. So nucleation happens when the temperature is cooled below the melting temperature, and then crystal has the lower free energy than the liquid, which provides this driving force. Meanwhile, because once you have a solid generated from the liquid, you always create a solid-liquid interface, which is always energetically unfavored. Therefore, these two factors putting together contribute to a nucleation barrier. So classical nucleation theory has been a very good theory to describe this simple picture and derive the formulas to calculate the nucleation barrier as well as the nucleation rate. And while you can see from these equations, it's related to so many quantities to derive this nucleation rate. For example, especially this chemical potential, which is hard to measure. And what's more important to measure is this solid liquid interfacial free energy. But there is no way to get this from experiments, and to mention this high PT, high pressure and temperature conditions. But nevertheless, people actually made some estimation using the different experiments or calculations to get all these quantities. And what they find is actually a very surprising results, that liquid core has to be supercooled by more than 1000 Kelvin so that the solid core could nucleate. So clearly this is a contradiction to the real situation, because considering the liquid core was cooled like 100 Kelvin to 200 Kelvin per billion year, this means it has to be there for more than 5 billion years, even longer than the Earth's age. So this is clearly a nucleation paradox. So, but what we should be careful here, because all these quantities was determined from this nucleation rate. And the nucleation rate, as I said, is very sensitive to the input parameters. So if you don't have a good estimation of this parameter, you probably get very wrong results, because you note this exponential term and this cubic dependence. So therefore, we plan to use DFT calculation with the potentials to perform molecular dynamic simulation to really see what is the nucleation rate of iron under this core condition. So here we bring this first, to simulate the nucleation, you have to have a very large simulation cell and also the very long time scale. So therefore, we develop this EAM potential, even though it's not well machine learning, but it really achieves a very good description of iron under the core conditions. So we mainly fit two quantities. One is the latent heat, which is very important for to study the solidification, and the other is the liquid structure. So here is the comparison of this latent heat for BCC and HCP iron with ab initio data and the classical molecular dynamics with the EM potential. And this is the liquid structures. As you can see, it's indeed achieve very good fitting. And then we measure the melting temperature via this solid liquid coexistence, because we are able to run very long time simulation and large scales. So this is so far the most accurate way to measure the melting point, as long as you can achieve these large scales, because it actually account for all this high temperature effect, including diffusion in the liquid, in the solid, and the unharmonicities. So basically what you do is you put this solid liquid coexistent well-equilibrated samples at different temperature. If it's above the melting temperature, you will see the liquid side will go to the solid side, while if it's below melting temperature, the solid side will move towards the liquid side. So with this, you can determine the melting temperature. And therefore, we compared our results with experiments, melting curve. Of course, this experiment is very hard to obtain. So there is two curves here. One is from the diamond average cell at the lower pressures, and another is the shock wave data from high pressures. And our results actually fit very well to their data. And so with potential, we first actually determine what is the ground state of the iron, because this has been a really long debate. And what we find is that BCC phase is always has a lower melting temperature than the HCP phase, which indicates BCC is actually a metastable phase. But note that when you approaching the center of the Earth's pressure, which is 360 kilopascal, you actually see these two phases have almost same melting temperature, which means they have very similar free energies. One thing I should mention here, even though I cannot go to details, is that we recently actually find once you have a good potential, you can actually transform all this free energy data from the potential into ab initio. Usually this was done, so we use this thermodynamic integration, but usually this was done with the model system like Einstein crystal or the ideal gas. But this is not a real system, and you will have very hard convergence and also very sensitive to the size effect. But if you perform a classical, if you have a good classical potential, you will see that this transition, this integration is quite smooth from the classical side to the ab initio side. And this doesn't limit to any potential. You can do it with EM or machine learning potentials. So once with this technique, we can actually transform this free energy difference between liquid and solid from a classical system to ab initio system. And you can see under this cross section basically defines melting temperature. So basically, again, it shows that this classical potential almost provides same melting temperature with ab initio data. Now we have a good potential. What we can do with nucleation. So nucleation is a stochastic process, so which means it's very hard to simulate. What you just run brute force molecular dynamics at the experimental or real situation, what you will see is your system will just track in this pre-nucleation region. So you will see many small nuclei formed, but it will never grow just because the time scale difference between the simulation and the reality. So therefore, we use this persistent embryo method, which we developed a few years ago. So the idea is that we capture some of this precursor, which is before the nuclear cross the critical point, and then we add some spring force to constrain this, we call it an embryo. So in this way, this embryo will never remelt. So the only way for it is just to grow. For the other part, for the liquid or the growing crystal, there is no bias. So with this, we can actually force the simulation, force the sample to nucleate. But we also don't want to bias the system because what we really need is this critical nuclear size, which directly relate to the nucleation rate. So what we did is we put this spring constant as a dynamic one, which means it will change with the nuclear size. So as the nuclear grows, the spring constant will be decreased, and at when it's close to the critical point, it was removed. So in this way, we can actually get the nucleation happen on the real conditions within the simulation time scale. So once we reach this critical nucleus, we actually can find that it has an equal chance to grow or melt at this free energy curve. So which means that you will see some fluctuations when the system stay at this critical nuclear region. So if we plot the nuclear size as a function of the time, we can actually see there is a few patterns which can be used as a characteristic features that we determine this critical nucleus. So with this measurement, we can eventually obtain this nucleation rate. So this is what we got from simulations. And this was an initial estimation from purely classical nucleation theory I just showed you. So you can see that once we perform this molecular dynamics, and we actually find that this HCP nucleation rate is almost 40 orders magnitude larger than the previous estimation. So if we put it under the core conditions, we can estimate the incubation time for the core, under the core condition, and then we can get the required supercooling for the inner core to appear. So previous estimation is around 900 to 1000 Kelvin supercooling, undercooling, but our estimation is actually just 600 Kelvin. So if you remember, I just told you that there is a competition between BCC phase and HCP phase. So we also calculate this nucleation rate with the BCC. So what we find is that it's actually, even though it's a metastable phase, but it actually has a nucleation rate almost 20 orders magnitude higher than the HCP phase. And then if the system crystallizes at the BCC, it only requires 450 Kelvin supercooling. So which means that BCC is most likely to nucleate well before the HCP phase, and it does not require that large supercooling. So of course, this is just this is from the persistent embryo method, and we also prove this two-step nucleation scenario with the brute force MD. But of course, here we have to use a very, very fast cooling rate so that we can see the nucleation under the computer. So here we will apply a movie, and I have already removed all the liquid. And so this is a cooling with 100 Kelvin per nanosecond. By the way, the core is cool is 100 Kelvin by billion year. But we do see at a high temperature at the initial of the simulation. So you see all this little embryo appear and disappear. So the green is presents the BCC nuclei, while the red is presenting the HCP nuclei. But at a certain point, you will actually see a nucleus appear and actually already cross the critical region. So if we keep the simulation run, we actually find that quickly the BCC transforms the entire sample to the bulk BCC phase. But it also remains a little bit HCP in this matrix. So, and if we keep this simulation running, actually, you can see this HCP phase actually forms some boundary with the BCC, and it's actually slowly grows. And at a certain point, it transforms the entire BCC phase to a HCP phase. So basically, if we plot this enthalpy as a function of the undercooling, you will clearly see these two stages. So first stage is a transformation from liquid to the BCC, and BCC was so stable and in all these undercoolings, and then it transformed to the final HCP phase. So this kind of give us this scenario of two-step nucleation, basically that because HCP has a higher nucleation barrier, even though it's a ground state, so the system actually tries to transform to a metastable state which has a lower nucleation barrier, and then eventually go to the HCP. So this provides idea of this inner core nucleation process. Of course, we haven't really fully solved the problem because first, inner core is not just iron, but is with many light elements. So the effect of light element has not been included yet. So we are working on to generate potentials which can capture this effect of the light elements with machine learning. So another is a possibility of heterogeneous nucleation, but this has been proposed a few times, but the problem is we cannot find a suitable substrate to induce this heterogeneous nucleation under the core conditions. So next we go to the other work, which is the discovery of these iron-rich FeO compounds. So as I just told you that, so core doesn't, even though iron is the major part, but the core also contains other elements. The key evidence is actually from the laboratory measurement and the seismic data. So this PREM, which is preliminary reference Earth model, was obtained from the seismic results. So, this lines is actually measured. The density is measured for liquid and HCP iron from the experiments. You can clearly see a density difference about 10% for the liquid region and 5% for the solid region. So this basically gives the idea that there must be some light elements in it. And you also notice that there is a density jump at this from when you transfer from the liquid to the solid. And this density difference is much larger compared to the actual iron density difference. And this can be understood by the partition, because in principle, there could be different partition between the solid and the liquid. So because you have a liquidus line and a solidus line, so therefore these concentrations of these light elements in the solid and liquid could be very different. Therefore, it's most likely contribute to this kind of density jump. So the quick question is how we can describe these phase diagrams of iron with plus light elements. So this is really very hard, even though experimental people and the Kaufau people actually worked many years trying to put data together to generate this kind of phase diagram, but I believe there are still not ongoing works. But the proposed phase diagram is there. So the key idea here, so for example, for these three elements, sulfur, silicon, oxygen, people believe that sulfur and silicon do have this kind of solubility in the HCP iron, but oxygen looks very special. So it seems that there is no any oxygen could be mixed with HCP iron. Why is that? Actually, if you really look at the literature evidence, it's really from the calculations done on 1990s. So with DFT. So at that time, people actually trying to see if this kind of reaction could happen by calculating by performing the static calculations. So in order to simulate this iron-rich oxide, they actually proposed different models, for example, substitutional model or interstitial model. They even considered different prototypes structures. But what they find is that this formation enthalpy is always a very large positive value as in the entire pressure range. And they even find that the amorphous structure has a lower formation enthalpy compared to these solids. So that's the lead to the kind of conclusion that it seems the oxygen prefer to stay with amorphous iron instead of HCP iron. Of course, because from experiments, people keep trying to synthesize this iron-rich oxide, but hasn't been successful yet. So far, no report at this moment. But we recently, our collaborators actually find that they do see some signals of this kind of reaction. So what they did is they put iron and FeO and compressed in the diamond iron cell and use a laser to heat it at to high temperatures. Of course, they cannot fully reach the inner core conditions, but their pressure is fairly high. So what they find is that if they heat it to around 2000 Kelvin, they don't see any signal. But once the temperature could reach to 3000 to 3200 Kelvin, they actually find some additional peaks appears in the experiments. Similar things happens with iron and Fe2O3. But they couldn't get, so their laser heating is usually very short. So, so this kind of peak is always very, very small. So they tried to solve this peak with non-FeO compounds, but they couldn't. And so the feature of this kind of XRD is it has multi-peak very concentrated in a very, very narrow region. So therefore, in order to see if there is any iron-rich compounds there, so we perform the crystal structure prediction with this so-called adaptive genetic algorithm. So probably you know this genetic algorithm is to sample large phase space by match different structure, cut and pass different structure motifs. So idea here, but to accelerate the usual genetic algorithm, we put an adaptive loop here, which is to train a potential along with this crystal structure prediction. Of course, you don't expect this potential to fully capture all the energy space of all these structures, but because it's adaptive, the parameter of this potential changes with the crystal structure prediction, it actually can accelerate to the structure relaxation and energy calculation during the structure predictions. So this was initially developed by Rata and Kamin Ho. So with this scheme, we actually searched this iron-rich oxide under the similar pressure range as experimental people did. And we indeed find that there is a quite large phase space that this structure has a negative formation enthalpy compared to these two end members. And if we look at the structure, it's actually a very similar family. So basically, we can see that even though this has different iron and oxygen, but they all packed like a close packed structure. And so basically, you only have very different stackings between the iron and the oxygens. So we take out all these hexagonal lattice structures and to see if there is any chemical and structural ordering in the structure. So first thing we find that if we just look at 3 layers, we can see there is only 4 types of stacking. We never see oxygen, 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 or oxygen, oxygen, iron stacking. So basically tells us oxygen hate to stay with stack with the oxygen, annihilate oxygen. And then we also check the structure. So for 3 layers, you can have either ABA or ABC packing. For iron motif, there is most of them is ABA packing, which is essentially HCP-like structure. But if you look at oxygen, iron oxygen, it's 100% to be the ABC packing. So it again can be understood because so once you pack as ABA, these 2 oxygen would be very close to each other, so it wants to separate. So then we try to match this XRD with all these close packed structures. So we can see that we can put different this iron-rich oxide. They indeed can contribute to part of this XRD. So, but this is only single cells. So the question remains is that is there a large supercell can match all these XRD peaks? So that's why we perform this Monte Carlo simulation. Basically, we learned this lattice as a function of this oxygen concentration, and then we just randomly swap different oxygen and the iron layers with different ABC or ABA packing. So the only rule is we avoid any oxygen first and second neighbor structures. So we indeed find a very big supercell, which is contains like 42 layers that can, with very complex sequence of iron and oxygen layers, and they can all match these XRD peaks. So when we analyze the local concentrations, we actually find that even though the overall concentration is 2:1, it actually fluctuates along this C direction, which means that the system most likely is not fully reached to the equilibrium conditions, probably because of fast reaction in the experiments. And but still, we can see some domains close packed in this structure. For example, we can find this. We can separate this FEU to 2 domains. One is contribute to the first 2 peaks, and the other contribute the other peaks. And their interference eventually contribute to all the peaks in the for this multi-peak XRD. So this actually tells us that all this multi-peak feature is just because there is different stacking of iron and oxygen from the experiments. So with the refinement, we can fully solve these structures for both reaction. One is Fe plus FeO, the other is Fe plus Fe2O3. So with this evidence from both experiments and the calculations, we believe that there do exist these iron-rich oxides in reality. So here come to my summary. So first is we use this DFT and the EM potentials to simulate the nucleation process under the Earth's core conditions. We find that once we adopt this BCC phase, this 2-step nucleation scenario, it actually reduces the required supercooling to much small degree, much small value, which is more reasonable to sample the real core conditions. And then we also perform this adaptive genetic algorithm with DFT calculations to identify number of iron-rich ground states on the high pressures. And these structures show a common hexagonal lattice motif, and it will explain the XRD peaks. So this result indicates that actually there could be a large amount of oxygen can be incorporated in the HCP iron under the Earth's core conditions, which is very contradictory to previous understanding that no oxygen in the inner core. So future work will focus still using this ab initio method, especially potentials, merged with empirical or machine learning to understand how these light elements partition between the inner core and the solid core. And eventually we hope to have a ab initio type of phase diagram to really describe the light elements and the concentration under the core conditions. Thank you.
Thank you very much for this very nice talk. Do we have questions in the audience? No questions. Do we have questions on Zoom? Is Xingxi here? Maybe you can show.
Oh.
You should have. If you click Q&A.
Okay, I think. Which one?
Q&A.
Q&A. Yeah.
Oh, no questions. Okay, then, yeah, maybe I have one question. Maybe you can say a little bit more about the machine learning part, which you plan in future. What are your plans there?
Sure. So EM indeed tells us that it can well simulate this iron, but once we put oxygen and the sulfur and the silicon, the correlation is actually much reduced. So we do have difficulties to still fit the EM type of structure potential to describe these iron oxide interactions. So that's why we recently actually adopted the DP potential developed by Dr. Carr. And we do see that it had very good performance to describe iron silicon oxide under the core conditions. So of course, eventually we still need this thermodynamic calculations based on this potential. That means we really need a very accurate potential to capture this very little difference, because you do see that a little bit I think the energy scale is like tens of milli eV, which can change the phase diagram by hundreds of Kelvin. So this kind of accuracy we want to achieve. So that's why we are still trying to merge it with the machine learning type of potential. And another is actually so currently we are still using the PBE functional to describe this iron oxide, but people do say that there could be strong correlation there, especially at a high temperature. So you don't really know how this correlation changes with different conditions. So this is another thing we are trying to work with, especially with more advanced functional to describe this kind of situation. Yeah, that's it.
Okay, so actually we do have a question now from Cyrus. Yeah, the microphone is coming.
So you showed that there are a lot of these structures that have iron and oxygen in various configurations that have similar energy. What is the diffusion barrier for the oxygen in the iron, and is it expected to be kind of just completely disordered with all of these competing structures?
Very good question. So what actually happens is, I think last month there is a Nature paper, which is really to simulate how these light elements diffuse under this inner core condition in HCP iron. So what they claim is that hydrogen, carbon, and oxygen can all diffuse so-called superionic state under the HCP iron. So, but we do have some different ideas. Actually, what happens is when you put this oxygen randomly at this different SCP structure, you do see the superionic state. But we think that it's just because it's not the right structure. Because in literature, people still think that oxygen doesn't diffuse, doesn't go to the iron, so they don't know this kind of structure. So that's why. And what we did is we use one of our structure prediction models. We put this oxygen close packed with iron. Actually, we cannot find the so-called superionic state. So this is still ongoing. So we will perform some more calculation and especially simulation to see how this oxygen diffuse in the core conditions. So good question, but we don't have a final answer yet. Thanks.
Yeah, we have time for one more question. There's one in the back.
Thank you. It was a very exciting talk. Thanks. Especially, I didn't know anything about any of this, so thank you. So is it difficult to model iron with DFT? I mean, we hear many times that some people have difficulties and you have to do all kinds of tricks. So what did you do to model the iron?
As I said, all this calculation is still PBE, but we do, when I first job with Renata is to trying to simulate FeO transitions under the lower pressures. This kind of like a failure of usual DFT has been used as an example by many people. Actually, what happens is indeed, if you look at the low pressures, what you do see is you cannot, so FeO is an insulator, but if you apply the usual DFT, you will get a metal. This kind of failure there. And there do have many methods to correct this, DFT plus UDFT plus DMFT. But what we find is So when you go to the higher temperatures, and actually it looks like the strong correlation seems to disappear. So this kind of like approaching the classical limit, and you have the system seems more classical instead of strong correlation. That's why when we use this PBE, we compare with experiments, especially these melting curves, give us a confidence that SIMS DFT indeed provides very good results. But again, we cannot guarantee that until we try this. And another thing is this FEO, we also think it looks good when we compare with the experiments, but we probably need more data to support this idea. Of course, we do want to perform more advanced DFT in future with hybrid functional DMFT and this many body strong correlations. But at this stage, all evidence is that from as far as we know, it describes well, just PBE.
There was one question. We have time for a quick one. Oh, yeah.
So in your simulations for your two-step nucleation process, you've got like a finite system, right? And how big are the effects of, like, if you've got 2,000 atoms, or finite size effects a big issue? Is that something you can see?
Sorry, could you repeat it?
Yeah, the accent probably. So yeah, in your finite systems simulations with iron being a liquid and a solid, is finite size of your system a big issue in your simulations?
So you're asking about the final size?
Yeah.
Yeah, definitely.
The effects of the edges as well, things like that.
So you basically are asking whether this small final size will change the nucleation rate.
Yes. How much does that affect?
Yeah, definitely. And that's actually one motivation for us to adopt all these kind of potentials. So first, the thing is, what happens when you measure this kind of critical nuclear size? You can easily see that it can go to like thousands of atoms. So this is just a nuclear size. And the key idea to simulate this nucleation is you don't want one nuclei to fill the other nuclei due to these periodic boundary conditions. That is why you really want to keep a large simulation cell. I think Professor Michel Perrineau actually had a very good estimation that this nucleation rate will significantly change when you put your size smaller and smaller, simply because one nuclei fills the other nuclei, this solid will interact. So indeed, that's why we do need very large simulation cells. And so this is for nucleation side. For this melting point measurement with this solid liquid coexistence, is also very important to adopt very large supercell. The point is you have to make this interface is much smaller compared to your bulk phase. Otherwise, you are just simulating interface, right? But what you want is actually a large bulk phase and a little bit of interface so that you can see how this bulk phase changes with different kind of temperatures. So size effect is very important. That's actually the motivation why people use machine learning or these potentials instead of DFT. So, right.
Thank you.
Okay, then we are at the end of the session. Thank the speaker and all the speakers in the session. And now, actually, because we are finally back in person, we will have a conference photo. So we will meet outdoor, directly outside. Yes, the photo exactly. And afterwards, we will have lunch. And we will reconvene at 2 p.m.
Can we just hold on for a second? We need to take a group photo of all of us here. Just yeah. Let the photographer say. I should say. So how would you like us to be?
How do you want?
You just speak.
You can remain seated. Okay, I thought you want to go to it outside.
You want to go outside?
What do you want?
I can take one here. I cannot find the feathers. Okay, so guys, please remain seated. I cannot. I don't think we can do later outside if you want. 要不要在台上走？大家都上来了。
Hi, everybody. I think we should get started with the afternoon session. My name is Sophie Beck. I'm a postdoc at the Flatiron Institute, and I'll be chairing the session. We have a great lineup, so let's better get started. Our first speaker, when I come to the stage, our first speaker is Dimitri Basov from Columbia University, and he'll be talking about shedding nanolight on quantum materials. Please go ahead. Do you want this?
Which microphone do I use?
Which one do you want?
Okay, why don't I have this? Good afternoon. Good afternoon. I have. Oops, that was a mistake. Have an echo here, so I'm trying to It's muted. Okay, I'll just ignore the echo from this. It's slightly irritating, I agree.
Oh, but it isn't, right?
Yeah, everything is muted. In this one. Our remote participants hear us as well. So it's a privilege to participate in this workshop. So what do we do?
I just click show it. It's okay.
What do you want me to click?
Actually, turn off the.
It's off. Do I need to use this microphone?
Yeah.
Okay. Great. Thank you. I apologize for this audio thing. I would like to thank the organizers for the invitation. And I hope everyone can still hear me here and remotely. Let me start with the headline message. This talk will be about new optical measurements, a little bit about new physics of quantum materials, and also about new problems that we are trying to resolve in the electronic structure of the systems with the help of nano-optical techniques. I will talk about a new way to investigate the electronic structure, and we will harness polaritons for this work. Polaritons are hybrids of light and matter. These are composite quasi-particles built from photons and materials excitations. This is an artist view of a plasmon polariton on the surface of a 2D conducting surface. So it looks like a ripple of electron density triggered with light. These do not need to be necessarily plasmon polaritons. Any material excitation is providing this type of effect. Irrespective of the microscopic origin of polaritons, they are very compact. Their wavelength could be reduced compared to the wavelength of light by many orders of magnitude. So you really need to have nano-optical tools to see them. This antenna-based spectroscopy is our experimental tool. And nanolight that I put in the title of this talk is not just a buzzword, it's an experimental reality of our experiments at Columbia. So compactness of polaritons is nice, but more importantly, polaritons are not static. Polaritons can move. And again, irrespective of their microscopic origin. And it is this traveling aspect of this object that I would like to harness to the best of my ability to investigate the electronic structure of new materials. So experimentally, we gain access to polaritons using what we call antenna-based nano-optics. It's a hybrid of a light source and of a scanning probe. Usually we use atomic force microscopes for this. And with the help of AFM tip, we can get access experimentally to very short length scales. The idea here is that you combine scattered light only from the area underneath the tip. Even with commercial tips, you get to length scales as short as 10 nanometers. The tip itself acts as an optical antenna. It spreads polaritons in all directions. And here you see an image, the raw experimental data of plasmon polaritons on the surface of graphene. When we scan this thing, we go through the ripples of this standing wave on the surface of the sample. So in conventional spectroscopy, we usually learn new physics by studying colors, by studying how much light of a given color is reflected, transmitted, absorbed. And here we are beginning to do something else. We really will focus on the shape of this standing waves, of how they travel through the bulk or on the surface of materials. And these images, actually, they are very telling. To me, these images look very pretty. To you, they may look ugly, I don't know, but they contain quantitative insights. And from these images, you can extract the response function, its frequency and momentum dependence. And that's usually a good start to have conversations with theorists who like to calculate this response function in a very new parameter space now of high momenta, of broad frequency range, and of nanoscale. And the research that I'm going to present today is a collaboration with card-carrying experts in the electronic structure, Raquel Queiroz, who is here, and Angel Rubio and Andrew Millis also. Often, propagation of polaritons on the surface of materials is compared to what happens when you throw a rock on the pond. And I think it's a very good analogy. And let me show you the New York City version of this analogy. So we'll use the El Dorado building in the Central Park as a cantilever holder. And when light impinges on this cantilever and on the tip, you have very strong electric field at the apex of the tip, and it spreads these polaritonic waves in all directions. You can learn a lot about water by studying waves on water. We learn physics of new quantum materials by studying essentially the same type of waves on the surface of materials. So that's the key idea. So this is the outline. To comply with the purpose of this workshop, I will discuss two examples when these type of waves tell us something new about the electronic structure of materials. The first example is zirconium silicon selenide. This is a three-dimensional material that hosts two-dimensional Dirac-like electronic structure. And Yinmin Shao in our group observed a new kind of waveguide modes in this metal. It's that's essentially the essence of Yinmin's discovery. Metal supports propagating waveguide modes, and I'll tell you how they happen, how they're related. They're enabled by the electronic structure of this compound. This is the first time I talk about this data. Please keep it to yourself. Don't tell anyone. So this is still unpublished. Then I will discuss another experiment that also relevant to the electronic structure. This example pertains to graphene residing on ruthenium fluoride, and this interface enables a gigantic charge transfer between graphene and ruthenium fluoride. This actually was predicted by band structure calculations in the group of Rosa Valenti, and I will tell you how we quantify this process, and I will tell you about unresolved issues associated with this structure. So that's the plan, and let me go to this hyperbolic modes in a metal, in a nodal metal, and how we visualize them with the help of nano-optics. So hyperbolic response is a universal property of layered materials, and that's almost universally underappreciated. And it's quite common for layered materials to be anisotropic electronically, or lattice dynamics could be anisotropic. Excitonic response can be anisotropic. And there are frequency ranges where you have in-plane and out-of-plane optical constants of the opposite sign. So this is the formal definition of hyperbolicity. So what's so special about hyperbolic media? There are many special things about it. And most commonly, when you have a medium with a negative dielectric function, this media does not allow you to have propagating waves. Light bounces off. Again, there is a New York City illustration of how, that's why metals are shiny, and this is a local illustration of metal shininess. On the contrary, hyperbolic media support waveguide modes that can travel through bulk of crystals. These are very special modes. The relevant isofrequency surface is a hyperboloid. That's where you get the names of these materials. There are many special things about it. First of all, this infinite wave vector enabled by this open surface. This allows us to develop a very new class of imaging devices. The notion of hyperbolicity came from physics of plasmons. It was explored in metamaterials. And in our group, we discovered propagating waveguide modes in an insulator first, and a semiconductor next, and I will show you results for a metal in just a second. So this is an idea of this experiment. We put a golden disc underneath a crystal. It's subdiffractional, it's very small. We illuminate it with infrared, long wavelength infrared light. And then these edges of the disk launch this propagating polaritonic waves that can travel inside the crystal. The origin of hyperbolicity in boron nitride, these are our vintage data for boron nitride from 2014. The origin of hyperbolicity here is in anisotropic lattice dynamics. HBN supports two bands of photons in plane and out of plane in different frequency ranges. Normally, insulators are opaque in the infrared region, but HBN, because it's hyperbolic, it supports this propagating mode. These propagating polaritons travel along conical trajectories, just like rays of light, but they're deeply subdiffractional rays of light. And of course, they can only live inside the crystal. So in order to visualize them, we need a nano-optical probe. The purpose of this optical antenna is to outcouple these modes once they reach the top surface, and then we send light to the detector and we detect this, and this is the raw image. So one disk creates these two characteristic hot rings on the top surface that we visualized. So, and since 2014, there was always a question whether these type of behavior can be supported by a metal. In principle, it can. In practice, this hasn't been observed before very recently, before the work of Yinmin Shao. And a candidate material we thought would be good for this type of experiments is zirconium silicon selenide. A few years back, Leslie Shoup, who is now at Princeton, she discovered this very interesting class of materials that supports Dirac-like electronic structure, essentially two-dimensional electronic structure in 3D host. And the nodal regions are connected with the line, and so that's why these metals are often referred to as nodal line metals. They possess interesting surface effects. The surfaces may be topologically non-trivial or not. This is sort of a topic of a discussion. A few years back, again, Yinmin Shao has done optical studies of these materials. From the analysis of the Drude weight, he concluded that the electronic bands are strongly renormalized in this class of materials compared to band structure predictions, and this renormalization can be taken as a measure of the correlation strength. So by this measure, zirconium silicon selenide is actually a fairly strongly correlated material. So this combination of 2D structure, reduced dimensionality, correlations and topology was an interesting mix, and Yinmin Shao decided to perform studies of these material polaritons in this material, and I'll go straight to this hyperbolic modes that he has discovered in this compound. Again, we are repeating the same experiment. We are putting a disk underneath the crystal that will act as a launcher of these polaritonic waves, and we'll try to detect them with a tip on the top of the crystal. This is an AFM image of a real structure. The crystal resides on the right of this image. And now I overlay an optical nano-infrared image, and you see along the edge of this structure, you see two hot rings that Yinmin has detected. So this is consistent with conical propagation of rays, hyperbolic rays. These are plasma polaritons in this case. And Yinmin has performed a systematic study of the thickness dependence of these modes. These ray-like conical trajectories imply that the separation between these rings is expected to be enhanced if you have thicker crystals, and that's exactly type of scaling that he has observed. Yinmin has carried out systematic studies of this effect as a function of frequency. And I show only a small segment of this disk now, but with data taken at multiple frequencies, and you see that the separation between these hot objects is systematically enhanced. So these data establish the hyperbolic response of this material. So what's these nano-imaging data allow us to obtain the dispersion, frequency momentum dispersion of these waveguide modes. And that's what's plotted here. This first line with red dots is a characteristic of any metal. This is, can be produced by surface plasma and polaritons, but then at higher wave vectors, you see higher order modes that are a signature of hyperbolic electrodynamics. So let me connect this to the electronic structure of the material, and it helps to look also at the far field reflectance that Yinmin has previously obtained for zirconium silicon selenide. This is a spectrum of the real part of the conductivity, dissipative part of the conductivity as a function of frequency in wave numbers. These are jargon units that spectroscopists like to use. 10,000 wave numbers is approximately 1 electron volt. So at the lowest frequencies, we find a Drude peak. That's a very good thing for plasmonic behavior. But then this Drude behavior is followed by a flat conductivity, flat frequency independent conductivity that is in fact a signature of a Dirac-like system. And we established that long time ago for graphene, maybe 15 years ago. So now this flat conductivity is actually very bad for propagating modes. And that's because for propagating modes, you want a high ratio of sigma 1 to sigma 2. And this flat conductivity is not that great for this because sigma 2 due to flat part is relatively small and sigma 1 is finite. So you get over-damped excitations. But then if you go to even higher frequencies, something else happens. And then the conductivity drops to a very low value. This is highly unusual behavior. This is, maybe the first time we are seeing this in many materials. And this effect is, so the flat part is attributable to the Dirac structure, but this drop to the conductivity can be understood quantitatively in terms of gap opening in the nodal line spectrum. Because of this gap opening, the conductivity goes down. And this has very interesting plasmonic implications. So because conductivity's real part goes down, by Kramers-Kronig, you get strong boost, strong enhancement of the imaginary part of the conductivity. And the ratio of sigma 1 to sigma 2 goes through the roof. In fact, this material shows the highest of all known values of sigma 1 to sigma 2. And that's why it supports the waveguide modes only in the frequency range where this behavior is seen. So this result also shows a good approach, perhaps, for band structure engineering of plasmonic responses. It's not the first time when interband processes interfere with plasmonic responses, and there is a huge community that tries to harness these plasmonic effects for all sorts of applied reasons. And the usual approach to get rid out of interband behavior is just to move them out of the frequency range of your interest. And this approach, this data by Yinmin Shao offer a slightly different strategy. You, in fact, can embrace the interband conductivity, provided you can engineer this cliff-like drop. And if you can do it in the frequency range of your interest, not only you get propagating modes, but you also get a boost of your plasmonic behavior. So let me tell you a little bit about this interface of graphene with ruthenium chloride. And right from the start, I would like to acknowledge numerous discussions with Ken Birch and Eric Hendrickson. In fact, it was Eric's paper from 2019 that in some ways has started the field. He investigated this structure with graphene residing on ruthenium chloride, and he observed high conductivity, and he attributed this effect to a strong difference between work functions of the two surfaces. And in parallel with that, calculations by Rosa Valenti have predicted that this interface is expected to be metallic with a fairly large Fermi energy, maybe half electron volt below the Dirac point of graphene. And these calculations also suggested the direct experiment that we can do harnessing plasmonic probes to investigate this behavior. So a decade ago, we established that the periodicity of plasmonic fringes really allows us to quantify the magnitude of the Fermi energies. Essentially, the wavelength of these plasmonic features scales as the Fermi energy. And so this experiment, this nano-imaging experiment, is the direct measurement of the Fermi energy and is the direct probe of this unusual interfacial band structure. And that's what we did. So this is the work of Dan Reza and Sarah Shabani more recently, and of many collaborators at Columbia. This panel shows nano-infrared image that Dan has obtained. Blue line is the physical edge of the crystal, and that's as he moves with the tip in the interior of the crystal, he is observing many of these fringes. then has carried out systematic studies of the dispersion of these features by performing measurements over a broad frequency range. So the vertical axis is essentially laser frequency. The horizontal axis is 1 over periodicity that he reads from his images. So that allows him to extract this dispersion. And there is one single parameter that's behind this dispersion is the Fermi energy. And that's how he extracted this gigantic Fermi energy for this interface. So in addition to this parallel line fringes, he observes this circular pattern. And our understanding of the circular pattern is the following. We think that around this circular patterns that we don't think we see that directly in our images. Graphene forms a little ripple over ruthenium fluoride. So the distance is enhanced. Charge transfer process is a very short range process. And so this dot region appears to be charge neutral. And it acts as a scatterer of plasmons plasmon polaritons that we visualize here. So together with hypasopathy, we try to inquire how sharp is the barrier between doped and undoped regions through this charge transfer process. And we harnessed STM for this. This is work of Sarah Shabani. And she concluded that these are actually extremely sharp barriers. Around this ripple, graphene is a little bit doped, is n-doped here, and then above this barrier, the Fermi energy drops deep below the Dirac point. But the width of this barrier can be as narrow as a few nanometers. So this allows us to create very sharp, abrupt p-n junctions on the surface of the structure. There are 2 unresolved issues in these experiments, and then I will conclude to stay on time. So first, what happens to these flat bands? This band structure predicts the drop of the Fermi energy. This band structure also predicts these flat bands. And we search for them optically, nano-optically, and we search for them with STM, and we find no evidence for these flat bands. Maybe somebody in the audience has an answer. We would really appreciate the answer. The other part of the story is what happens to ruthenium fluoride side of the interface. Ruthenium fluoride is actually not a randomly chosen material with high work function. It's a very interesting system. It's perhaps one of the leading candidates for so-called spin liquid behavior. And when spin liquids are doped, there was this great hypothesis by Phil Anderson, they may become high temperature superconductors. So ruthenium fluoride has to be doped in these experiments. We did our best to search for signatures of the electronic transport on the ruthenium fluoride interface. We have some hints of that, but with an emphasis on hints, not solid evidence yet. So these are 2 unresolved issues that will be the topic of the future work. So let me summarize. This talk was about polaritons and how polaritons inform us of electronic structure of interesting quantum materials in new ways. I think with these experiments, we have barely scratched the surface of what nano-optical methods could produce in this line of work, and we are beginning to reimagine what we can do next, what kind of materials we can study, what kind of problems we can address, what kind of nano-optical experiments we can expect. It's 2:30, I'm right on time. Thank you very much for your attention.
Thanks so much for the beautiful talk. Right, questions? Yeah, okay.
So how long-lived are these polaritons? So do you expect to see the effect of the hyperbolic behavior if you have a very thick sample, or you're using the fact that it's quite thin?
I think we need to define what we regard as very thick. So these crystals are about tens of nanometer, maybe up to 100 nanometer thick. So they are bulk from that point of view. Can we guide this way through a meter of zirconium silicon selenide? If that may be difficult. So, and in this first generation of experiments, there are substantial losses. You sort of see that these fringes are not as pretty as some other fringes that we see, say, due to hyperbolic phonon polaritons in ruthenium fluoride, for example. But we believe these are manageable things, and so there is a lot to be done on the improvement of crystals, and you know, we haven't even tried to go to low temperature with these experiments when losses, phonon losses, will be reduced. So losses will always be there, but this is not a performative breakthrough. It's just a conceptual advance.
Great, thank you.
More questions?
Thank you for the fascinating talk. So my question is on the first part of the presentation. I have read the exciton-proton condensation at a particular temperature. Do you think is it possible for phonon protons too? Just curious.
Is it possible for phonon polaritons to condense? Well, never say never, but exciton polaritons condense. One of the reasons why it's relatively easy to see their condensation is that exciton polaritons are extremely light quasi-particles. For condensation for BEC, you want to start with a very light object. So from that point of view, phonon polaritons wouldn't be my first choice. But who knows?
More questions?
They're beautiful experiments. So I just wanted to talk about the questions you posed at the end about your ruthenium chloride graphene system.
Yeah.
So do you see the narrow bands before the graphene's there if you do surface spectroscopy? Or are they something that lives at the interface only?
Well, so I think your question is about pure ruthenium fluoride. Well, if you do spectroscopy on pure ruthenium fluoride, you have a material with a gap of 2 volts. So you see all sorts of bands that are consistent with some calculations of electronic structures, but they appear in a very different energy range. So it is this interfacial physics that brings relevance of these states to low energy physics. In pure ruthenium fluoride, there is still, I think, a debate of what is the lowest energy absorption process, whether it's excitonic or not, or whether this is a band gap. So there are some unresolved issues there as well. But here this flat bands due to ruthenium fluoride, they are sort of in these calculations, they are in the face of anyone doing low energy experiments. If I look at these plots, but we don't see them in our measurements yet, and so that's a little enigma we are facing with.
And this is a traditional band structure calculation?
Well, that you need to ask my card-carrying collaborators. I think they tried several methods, and they roughly produce very consistent results. There are subtleties in which they disagree, but these are calculations by Angel Rubio. To me, they look identical to what Rosa Valenti has done, but there may be subtleties that escape my sort of level of understanding these subtleties.
Thank you.
I think we can take 1 or 2 more questions since we started late. Okay. Maybe you and then you can ask.
Really beautiful. I'm wondering about defects. They're probably there, right? And if they're there, they probably change the situation pretty dramatically.
So, while defects is a very
I'm
broad
thinking about
band.
HBN in particular. You know, hexagonal boron nitride, not this one, the one you showed earlier.
Yeah. Well, I'm sure they're there. So in some form. So we can try to quantify a little bit the role of defects. And for example, we were able to extract, so one measure of this is the loss of plasma polaritons. And we concluded from this work of Dan Rieser that if defects scattering plasma polaritons are there, they're not really overwhelming this data. So, but defects are always there. That's why we started doing STM experiments with Abhay Pasupati, my colleague in the physics department here across the street. Whether these defects can wipe out these flat bands, I don't know. It seems to me like a really major effect along with the drop of the Fermi energy. And the drop of the Fermi energy is definitely there, even if the defects are present.
Yeah, but defects actually give you these mid-gap states, right? They may actually promote it.
Well, the problem is that we don't see mid-gap states.
Okay. Okay.
Okay, one final question.
Thank you for this beautiful and inspiring presentation. My question is more basic. If I remember correctly, plasmon are collective vibration of electrons in crystals. So when I look at this picture, I ask myself, what modify the way of vibration of electrons? For example, I look region 1, region 2 there, and region 3. And since when she was asking her question, I was about to say, is it not defects, or what modify the way of vibrating of that electron cloud?
Yeah, thank you very much for this question. And I had to rush a little bit through this part of my talk, and I'm so glad to have your question. You are absolutely correct with defining plasmons. So what we are doing in our experiments, we are really operating with plasmons coupled to infrared light, and we make, hybrid modes that are half light, half plasmons that can travel on the surface of these crystals. So that aspect defines many of the features that you pointed out correctly in this image. And so the dominant feature is this standing waves launched by the tip that travel to the edge of the structure, come back, and they produce this standing periodic pattern. But also the circular ones, and that's where the graphene becomes undoped, electronically different from the rest of the interior of the crystal. So this little dot acts also as a reflector of the plasma, just like, so this is an electronic reflector. Thank you for pointing this out. This is a physical reflector, but for standing waves, they kind of produce the same character. And along the edge of the structure, there is yet another plasmonic mode that I didn't discuss in details. These are so-called edge plasmons that they have a slightly different wavelength because only half space is occupied by electronic plasmonic medium, and the other half is an insulator. So they still behave as waves, but with a slightly different wavelength. And thank you for the question.
Okay, thanks. That's the speaker again for this great talk. And let's continue with the next speaker. So our next speaker is Feliciano Giustino from University of Texas, Austin, and he'll talk about ab initio description of electron-phonon interactions.
Okay, good afternoon, everybody. Apologies for the delay, but there is a lot going on here. Actually, you will see if you come presenting. So this is going, I guess, on Zoom, then streaming on YouTube, and yeah. I mean, it's pretty impressive, actually. My name is Feliciano Giustino, and I'm from UT Austin. The title of the presentation is Dynamic Rashba-Dressel effect. So it's not about generic electron-phone interactions. So what I would like to do is to tell you a little bit about work that we've been doing in the area of spin-phonon couplings. So we've been working a lot on phonons and electron-phonon interactions, and a couple of years ago we wanted to take a dip into the world of spins. So that's the result of that effort. And I should say that this is one of the rare instances where in my group I work with only one person. So this was Martin Schliff. He was a postdoc in my group, and then he decided to become a software engineer at BASP. So he's an outstanding scientist, and we did a lot of interesting kind of maths together. I'll try to explain what we did here now. I assume that not everybody is familiar with the Rashba effect. So we'll give you a very pedagogical introduction in the way you would do for undergraduate courses. So the Rashba effect essentially is the splitting of doubly degenerate bands in certain systems. And the original work was done by considering essentially a two-dimensional electron gas. So you consider a plane here where you have a free electron gas. So you have parabolic dispersions, and these bands are doubly degenerate in spin, okay? Then what one does is to consider spin-orbit coupling. So you would have a term like that to be added to the Hamiltonian, and this is the gradient of electrostatic potential. So to activate this term, you need a potential. So in this conceptual experiment, Rashba considered an electric field that points perpendicular to the plane, all right? So if you replace the field here, the expression simplifies quite dramatically. So this is the polymatrix, this is the electron momentum. So the expression becomes something very simple. It's just the product of a polymatrix along x times ky, so k is the electron wave vector, minus sigma y kx, okay? So that's just a 2x2 matrix, and one can diagonalize that together with the standard kinetic energy of the free electron gas, and you obtain essentially a modification of the band structure that consists very simply of an addition of a linear term, okay? And that results into the displacement of this original parabola, basically on this side or on this side. So basically you have a splitting of these energy bands, all right? So that's what's called the Rashba splitting. And the Rashba energy is the separation between the bottom of this kind of valley and this intersection point. So that's one of the aspects of the Rashba effect. There is a second aspect which is also more interesting, and that becomes evident if you take this triple product and you bring the polymatrix to the left. Okay, you just use the rules of the triple product. Since the polymatrix represents essentially the spin of the electron, you can rewrite this Hamiltonian as a product of, let's say, magnetic spin dipole moment in a product with the magnetic field. Okay, and this magnetic field is just a fictitious magnetic field, which is defined as the electron momentum times the, let's say, the direction of the external electric field. So this is interesting because if you try to plot this object in a two-dimensional plane, you find a vortex. So this is the so-called effective Rashba magnetic field, and the Hamiltonian to obtain is a standard, magnetic dipole interaction Hamiltonian. So as a result of this Hamiltonian, you would find essentially that you minimize the energy when the dipole aligns with the magnetic field, so it rotates with the field, and you maximize the energy when that goes against the magnetic field, so anti-parallel, okay? So since the electron has a charge of minus, a negative charge, in practice, the spin of the electron will want to align either anti-parallel for the lowest energy band or parallel for the highest energy band. And that means that if you look at this band splitting, the lowest band here corresponds to an electron spin rotating counterclockwise, and for the highest band, the electron spin rotates clockwise, okay? So this is something that has interested a lot of people for many, many years because it can be used to manipulate spin textures in semiconductors. So one of the main applications that people have been thinking of when talking about the Rashba effect is the DataDAS device. So the idea here is that one wants to control the spin of electrons using ferromagnetic source and drains in a FET configuration, and trying to let electrons go through or stop them by using the orientation of the spin of the electron and by changing this orientation, how they travel across the channel. Okay, so if you start to spin parallel to this source, and you end up with spin that is anti-parallel, then you cannot go through, and this is essentially off state. Otherwise, you would have the opposite scenario where you have the on state where the current goes through. So how to change the spin essentially alignments in this channel? So the idea using the Rashba effect is to exploit the fact that spins precess in the presence of a magnetic field. Okay, so I told you that if you apply an electric field pointing, let's say this way, and an electron is propagating this way, you would have a Rashba field pointing this way, and therefore the electron spin will precess, essentially around this axis. So that means that if I apply a gate voltage here, there will be an electric field along this direction, and the electron spin will precess in this plane. All right, and then with this the intensity, sorry, the strength of the electric field, you can control the frequency of the precession, and therefore whether you end up parallel or anti-parallel. So that's one of the main applications. And this is trying to realize the Rashba effect using a device. There are cases where actually the Rashba effect can be seen in materials. So it's an intrinsic effect that actually has to do with the internal electrostatics of the system. So this is, for example, bismuth tellurium iodide. Is a system that does not have an immersion center. So there is an intrinsic polarization of the system. And this results into a Rashba effect that you can see via angle resolved photoelectron spectroscopy. So this will be one of the parabolas, and this will be the other parabolas. And the other signature is that if you do an energy cut, you will see instead of just one circle corresponding to parabolic dispersions, you will see two concentric circles, all right? So to my knowledge, this is the system with the largest Rashba splitting, so the order of 100 millivolts. So this is quite, let's say, low energy physics. So one has to, to develop techniques to look into these things, experimentally in order to exploit them. So that's all that was known until, a few years ago. And then, the thing that we were interested in is whether we can discuss how this effect relates to phonons. So the idea was very simple. So you have, direct optical transitions in semiconductors, and you also have phonon-assisted optical transitions. So you have the standard Rashba effect. Can one invent or can one think of a phonon-assisted Rashba effect? Okay, so that's a question we wanted to work on. To understand the answer, one has to first, discuss how this shows up and what are the conditions needed for the Rashba effect. So this is something that you probably see in your first course on solid state physics. So the idea is that if a system has a parity, so that means immersion symmetry, and you change the wave vector of a band electron, so the eigenvalue doesn't change, all right? The other observation is that if you have time reversal symmetry, for example, a system without an applied magnetic field, if you swap time, so if you change the direction of the propagation of the electron and the spin direction, you also have the same eigenvalue. So this is what in chemistry people call the Kramers degeneracy. So if you combine those two, you discover something that we all know when we do DFT calculations, and that's the fact that if you take the two spinors corresponding to the same wave vector, they give you the same energy. So you have doubly degenerate bands. That's kind of trivial, right? So now so that means essentially that a Rashba effect is forbidden if you have a parity in time reversal, right? Central symmetric non-magnetic system. And the question is now, if you think about vibrations of the lattice of a crystal, so at every given time, the atoms will be slightly off their equilibrium position because they are fluctuating, right? So at each time point, you will have a situation where the symmetry of the crystal is kind of broken. So one could say that for these snapshots, you are breaking parity. And therefore, this condition is no longer satisfied, and therefore maybe you could have a Rashba effect caused by phonons, all right? So this is not something that we came up with, actually. We started working on this because there were many suggestions of this effect in the literature. So in particular, we came to this because we've been doing work on these kind of systems. So these are a hybrid organic, inorganic perovskites. So if you never met these systems, these actually became very popular 10 years ago because it was discovered that they are extremely good photovoltaic materials. And the idea is that these are perovskites in the sense that they have lead in the center of the octahedra, iodine at the corners. These octahedra connected by the corners. And then that's, for example, like lead titanate or strontium titanate. So the key difference with respect to standard perovskites is there is a molecule in the middle. So this is metal ammonium in this case. And what is strange about these systems is that if you excite electrons from the valence to the conduction, so you have basically photoexcited carriers, they live a long time, okay? So they live something of the order of, I think, 10 microseconds, which is quite incredible if you think about the fact that these are kind of hybrid organic inorganic systems. There are many defects around. So people have been thinking about what could be the possibly the origin of these very long lifetimes. And for example, one of the proposals at the very beginning, Andrew at UPenn, was that in this system there could be a Rashba effect, and the Rashba effect transforms the system from a direct gap semiconductor to an indirect gap semiconductor, okay, and that endows the carriers with longer lifetimes. Then other proposals were, for example, from the group of the Angels, where they observed that if you do molecular dynamic simulations, at every time point, you find that the bands are split, okay? So you have some kind of Rashba effect. And therefore, the proposal was that the splitting might be, again, explaining why the carriers don't recombine that easily in the system. And then there were also experiments. For example, this is a circular photogalvanic measurement where they essentially they send circularly polarized light. And if you have a spin splitting, you should observe some kind of current. And they did observe some current, but only in one of the phases, the tetragonal phase of the system, and not in the orthorhombic phase, which is the centrosymmetric one, okay? So we wanted to try and understand whether actually one can really realize some kind of splitting using phonons. And we've been doing some, essentially some simple kind of algebra, but it's algebra in second quantized notation. So we'll drive you through the equations because they are quite understandable, I would say. So first of all, let me explain one point with a cartoon. Before I show this kind of cartoon where you have an atom, the bond has been moved from equilibrium because the system is vibrating. So you are not at the bottom of the potential, but you are somewhere off the bottom. So in this case, you would have a breaking of symmetry, right? And that's what one observes in molecular dynamics. However, we should keep in mind that when we do the FT calculations, we are making one approximation, and that's the fact that the atoms, essentially are, so the ions are decoupled from the electrons from Born-Oppenheimer, and they're also classical particles, okay? So if you try to bring back the quantum nature of nuclei, you realize pretty quickly that even if you are at zero temperature, so the distribution of the nuclei, so the probability distribution, it's symmetric, okay? So this would be a Gaussian in a harmonic system. So in this case, you cannot have any spin splitting resulting from atomic motion just because the quantum wave function is symmetric. So then one can ask, what happens if I consider an excited state? And if you have excited states of a harmonic potential, again, the density is also symmetric. So also in excited states, you cannot have any spin splitting. And then at some point one can say, okay, but what if I do a simulation of finite temperature? Well, finite temperature corresponding to performing a canonical average of all these scenarios. And what you find for this kind of cartoon model is that also in this case, you find a Gaussian. So also at equilibrium, at a finite temperature, you cannot have any asymmetry. So the spin splitting is also forbidden in this case, okay? So at this point, one could say, okay, that's done. So you cannot have any spin splitting. Well, actually, the problem is a little bit more subtle because in this discussion, I am talking about quantum wave functions, but there is a second approximation, which is even more important, is the Born-Oppenheimer approximation that I did not discuss, okay? So what we wanted to do is to try to figure out whether you can go beyond the Born-Oppenheimer approximation and whether maybe if you do non-adiabatic calculations, you might get some spin splitting. So the way we went about this problem is to try to define mathematically. So this is essentially a standard electron phonon Hamiltonian. So these are ladder operators as usual for the phonons. These are the electron creation annihilation operators. And these are the electron phonon matrix elements. So this is the usual Hamiltonian you see in any textbooks on electron phonon interaction. So the only difference is that now we are incorporating a spin orbit coupling. So you will see in these terms, the polymetrics, the del operator, and the momentum. So these terms in red are the only difference with respect to the standard electron phonon matrix element, okay? And the question is, what can we say about the possible spin splitting of states resulting from this Hamiltonian? So what we did basically is to try to construct a proof that there cannot be any spin splitting, even if you consider non-adiabatic effects, to any orders in perturbation theory. So what we did is to start from first order. So to first order in perturbation theory, what you need to keep in mind is that there are two spin degenerate states, because we are in a parity and time universal symmetric system. There are 2 states that are symmetric because of k minus k. So there are 4 states that are all degenerate. So one has to diagonalize a 4x4 matrix to find out possible spin splitting. And here I'm just showing you this matrix element by cleaning up some of this stuff and just leaving the most important part, which is the ladder operators. So if I look at this term, what this means is the following. So the first term here, Ks, is essentially me creating an electron out of the Fermi vacuum. So take a semiconductor with filled valence bands and empty conduction bands. So you create an extra electron in the conduction band. So this is not an eigenstate of the system, okay? It's a quasi-particle excitation. And then when you apply the ladder operator, for example, this one, you end up with a system which is, if you start from the ground state, this will be the same system plus 1 phonon, all right? Now, on the left-hand side, you have the phonon ground state, okay? So there are 0 phonons in the system. And therefore, when I combine them, this term with this term, I have orthogonal states, and the scalar product is 0, all right? So that means basically that these 4 matrix elements are all 0 simply because I have orthogonality here. And this can also be repeated in the same way to 3rd order perturbation theory, 5th order, 7th order, and so on, okay? So this is basically a way to say that you can prove quite easily that all odd orders in perturbation theory vanish. So you cannot have any spin splitting coming from these orders. So now the more complicated case is when you have even orders, and I'll try to explain why this is complicated. So if you consider even orders, so you need to diagonalize terms that are like initial state, perturbation, intermediate perturbation, final state. Now, the initial state and the final state have 0 phonons, if I look at 0 temperature, for example, but the intermediate state can have any number of phonons. So, okay, the reasoning that I used in the previous slide does not work in this case. So at this point, we had to do a little bit of algebra of the symmetry and of the spin phonon coupling to understand how this works. And in practice, it is easier to work out with some diagrams. So this term can be represented as a self-energy. You have incoming electron, an electron line in the middle, and an outgoing electron is the phonon line. And the red spots are the electron phonon matrix elements, okay? So what you can prove if you consider parity and time reversal is that if you have a matrix element, okay, and you swap the spins in this matrix element, so you do a spin flip, if the 2 spins are the same, you take a complex conjugate and you maintain the sign. If the 2 spins are opposite, you take a complex conjugate and you acquire a minus sign. So what that means for this kind of diagram, so suppose I consider a situation where the initial spin is up, the final spin is up, and the one in the middle is also up. Now, in this case, essentially, if I do a spin flip, this one will not change sign, and this one will not change sign. So what is going to happen is that I have +1 and +1. So this object remains essentially identical to itself. That's a tautology, is not very useful. If instead I consider a situation where I spin up here and spin down here, what is going to happen upon spin flip is that this acquires a -1, this acquires a +1. So in practice, upon spin flip, the entire object here takes a complex conjugate and changes sign. However, this matrix has to be Hermitian, okay? So the off-diagonal terms, the one corresponding to opposite spins, must be the complex conjugate of each other. So the result in practice is that this object is equal to minus itself, and therefore it must be 0. So the bottom line is that this second order self-energy must be diagonal in the spin index, okay? So you can have shifts, but you cannot have splitting. So now the interesting part is that the same reasoning can be applied to any even order in perturbation theory. In practice, just to show you, if you do a 4th order perturbation theory, one of the diagrams that pops up is this one with 2 phonon lines. What happens is that you always accumulate a -1 sign here, 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 whenever you cross a matrix element. And when you consider all the possible signs, again, you have -1 times the difference of the spins here and here. That means that if you have the same spin, the term is allowed. If you have the opposite spin, this term has to vanish, okay? So that means in practice that you cannot have any spin splitting to any even order in perturbation theory. So combined with what I say in the previous slide, what is the result here is that if you consider even non-adiabatic effects, so standard second quantized electron phonon coupling, you obtain a situation where the spin splitting is simply forbidden, okay? Now, what I just showed you has to do with 0 temperature, but it can be repeated, quite easily for any phonon eigenstate, and therefore it can also be extended to finite temperature using a canonical average. So the bottom line in practice is that the Rashba-Breslau spin splitting cannot happen in thermodynamic equilibrium, okay, coming from phonons. So, and this is actually as a consequences for this kind of perovskites, because that means, according to this analysis, is that you cannot observe any spin splitting in the system if you are in a centrosymmetric phase. So actually, this is consistent with what was measured by the group of Fauster in using circular photogalvanic effect, because they observed a spin splitting, below under 60 Kelvin, which corresponds to the above under 60 Kelvin, which corresponds to the tetragonal phase, which is non-centrosymmetric. And there was no spin splitting below under 60 Kelvin, which is the orthorhombic centrosymmetric phase. Okay, so this seems to be consistent with what has been observed in the experiment. So at this point, I could close the talk and say, okay, this is not possible, so we stop here. However, one can also try to go beyond that. And remember, one of the keywords that I used before, so I say that there cannot be any spin splitting at equilibrium, all right? So one question one might have is that, okay, what happens if I go beyond equilibrium? So if I go back to the first order perturbation, so this was the matrix element I showed you earlier. So you remember there was some kind of ladder operator here. So what was happening there is that this actually changes the phonon number of the ket here, and therefore it causes orthogonality, and this suppresses the matrix element. All right. So one way to avoid this problem is if I applied basically this distraction operator to the ket, I don't obtain something with a different number of phonons, but I obtain something which is a constant times the state itself. Because if that is the case, this state and this state will not be orthogonal anymore, okay? So now, if you remember your elementary quantum mechanics, you might remember that this equation actually defines what people call Glauber states or coherent states, okay? So the eigenstates of this operator are what we call coherent states. That means that instead of considering eigenstates of the phonon Hamiltonian, you have something that looks like a localized wave packet that is what in textbooks you see called as the minimum uncertainty wave packet. So that's basically a wave packet of nuclear charge that oscillates coherently around the equilibrium kind of configuration. So if you use coherent phonons, you have something where this is non-zero, and therefore you might have some spin splitting, all right? So the question at this point is, what are the rules of the game? So what kind of phonons you need to consider to realize this effect? So this just requires a little bit of thinking, and basically what we managed to show is the following. So first of all, you need zone center phonons, so near the gamma point. Otherwise, you cannot break the symmetry of the crystal, and that's essentially brings you to something that can be dealt with using light spectroscopies. The second thing is that one can prove that only odd symmetry phonons can play a role, and therefore you are bound to use IR active modes. And the third thing is that you can do some analysis to show that actually, if you consider longitudinal optical modes, they give a vanishingly small contribution to this effect. So really, the only option to realize a spin splitting that has to do with out of equilibrium phonons is to consider infrared active modes, as you could, for example, excite using IR pumps, for example. So the other thing that one can show is that you can calculate the Rashba energy directly using this spin phonon matrix element. So this is actually quite easy. You can use any code to do that. So you just consider phonons at the gamma point, and this gives you directly the magnitude of the splitting. So one can search for systems with the larger Rashba splitting. So let me now tell you a little bit about an application to this perovskite I showed you earlier. So if you move some of these phonons around, you can induce a dynamic splitting of these bands here. And what we basically did is to try to look for the modes that give you the largest possible splitting. So in this case, this is a system that is a PNMA structure with 48 atoms per unit cell, and there are exactly 20 IR active modes corresponding to the vibrational lead and iodine. So we scan all these modes, and essentially what we realize is that there are a few modes that actually have very, the largest splitting. For example, in the conduction band, there is a mode around 3 millielectromoles that give the largest splitting. So we focus on these modes just to anticipate possible experiments. And what you can find out essentially is that depending on the amplitude of this coherent oscillation, you may trigger a splitting which is as large as maybe 30 millielectromoles. So in this case, that corresponds to an elongation of the bond of the order maybe of 0.1 angstrom. So that's about maybe 4% of the bond length in the system. So this should be kind of achievable in experiments. So just if you're wondering, this is a rocking motion, and this is a bending motion of the octahedron in this case. So in practice, what we're trying to say is that, yes, you can possibly realize, at least theoretically, a spin splitting if you use coherent phonons. You can control what kind of amplitude you have by changing the amplitude of the vibration and by looking at specific vibrational modes. The next question is, this is about the splitting, but what about the spin texture? And this is where things get more interesting. So for the spin texture, what we did essentially is to do K.P perturbation theory using second quantization, okay? And the result actually, the maths are a bit ugly, but the result is quite neat. So you obtain that your spin texture can be described with a very simple Hamiltonian looking like this. So this is polymatrix, electron wave vector. And this is essentially a 3x3 matrix that has to do with spin phonon coupling. So in practice, one could ask, okay, what kind of spin texture do I get? Do I get a Rashba splitting in this case or something completely different? Well, it basically depends on the shape of this matrix. So what you can show that if this matrix is an anti-symmetric matrix, you get exactly a Rashba splitting. So the spin texture essentially rotates like a vortex like this. If this matrix instead is a traceless diagonal or traceless symmetric, you get something that is called the Dresselhaus splitting, Dresselhaus spin texture, which essentially is a kind of a quadrupolar spin texture like this. But there's also other options. For example, if this matrix is isotropic, you get something like a wild texture. So this would be similar to the texture of the zero spinning graphene, for example, or in a wild semimetal. Okay. So in other words, what this seems to say is that if you use phonons to induce a Rashba splitting, you could have actually more degrees of freedom than you actually do by just looking at crystals, at equilibrium. So now let's see, what is this matrix? So this is getting a little bit ugly, but I want to tell you, the whole story. So to decide what kind of texture you want to get, you need to look at you need to calculate this matrix. And in practice, this is the shape of the matrix. I mean, I'm putting it there just to explain the process. So what we do is to look at what you have inside here. This will have some kind of irreducible representation. From that, you can decide what are the possible couplings between these two spinors, and that decides exactly the shape of this matrix. Okay. So how do I know the irrep of this term in the middle? Well, I need to start from the reducible representation of the phonon mode. From that, I can work out the combination with the del operator and with the polymatrix. This gives me other irreps. And then from that, I can decide what are the possible couplings that will determine my spin texture. Okay. So in our case, for example, if you consider the B2U mode, you obtain a spin texture that is going to be probably Rashba. And if you consider the AU mode, you're going to get something that is going to be probably something like a Dresselhaus. So just to show you that that works, we basically perform calculations of the spin texture for the B2U mode that I just mentioned. And we were expecting a Rashba texture. So this is basically a color plot of the spin texture of the conduction band bottom of the system. And you indeed find two counter-rotating spin textures in this case. So that's a collapsed view of these spins that go this way, essentially. And if you instead consider the AU mode, I was expecting a Dresselhaus texture. And in fact, the spins up on here, then here inside, and then outside here. And the ones in the inner circle essentially go the other way around. So you can see this collapsed view here, okay? This is kind of an anti-vortex. So that's essentially what corresponds to what we have predicted just by using group theory. And the bottom line of this is essentially that if you have a system where you can pump phonons coherently, then it might be possible to induce selected spin textures dynamically, by essentially using some simple rules of group theory. So that's actually something that we consider interesting. So just to give you an idea of what could be done, so one should be able to pump essentially light, in a terahertz range, because these phonons are all in the terahertz range, and then one should be able to observe it. Maybe one could observe, photoluminescence, because if your conduction band bottom and valence band top split, dynamically, you should observe some kind of quantum bits in the photoluminescence. Or maybe one could look at the time resolved ARPES. And there's been experiments in this direction. For example, this work by the Jingwan Lag at the Ames, they were looking precisely at this problem. Essentially, they were pumping the perovskite and then looking at the photoluminescence, and they've been observing things like bits in the light emission from this material. So that kind of corresponds to what we are saying. So the only difference between what we're saying and their work is that they think that they have this is being caused by a Raman phonon. In our case, we think that there cannot be a Raman phonon because it has to be a odd parity. And in a central symmetric system, you can only be either Raman or IR. You cannot be both. So apart from the mode assignment, probably this is the most closely related thing to what we are proposing. So the other thing one could do is to look at time resolved ARPES. So in this case, basically, these are kind of static experiments where you see, kind of a circle. Imagine a parabolic valence band at gamma. So if you do an energy cut, you get a circle. So what should happen if you pump a coherent phonon and you have a spin splitting? So this should become two concentric circles, like in the example of bismuth tellurium iodide that I was mentioning earlier. So these things actually are in principle possible, but actually quite difficult experimentally. So we're now discussing with a young colleague at UT, Edoardo Baldini, an experimentalist, ways to bring essentially a terahertz pulse in a way that can be then subsequently measured by ARPES, which apparently is something quite difficult. And how much I have? Okay, so let me just maybe I'll spend 1 minute just to say that so much of this work on electron phonon coupling has been done around a software that we develop. Actually, it's called EPW. Maybe some of you already have seen it. So the way this works is essentially that it is now a core module of the Quantum Espresso package. It takes wave function and density and phonons from Quantum Espresso. It takes information from 1A90 for 1A functions, combines them to deliver some a number of properties that has to do with electron phone interactions. And now the number of properties has been expanding in the past maybe 10 years. And in particular, we have many body superconductivity, like full band Eli-Ashberg equations, Boltzmann transport, including magneto transport. We will be releasing a module to do polarons, next week, and then one can do ARPES, finite temperature bands, phone-assisted optics, and many other things. And this is a collaboration that now is growing and involves quite a number of groups now in the US and in Europe. I think in the interest of time, I will just close here, and I will not tell you more about that. Let me just say that we will be having a school on electron phonon physics in Austin in a couple of weeks. And so now this is going to be an in-person school, so the registration are closed, but we will be streaming the lectures in the morning through Zoom, essentially. So we will be sending an announcement shortly about how to access these lectures. And this is the the current group. I've been in Austin for 3 years, and this is the group as is. As of last month, I would say. So thank you for your attention.
Does it work? Yeah. Thanks so much for this great and very insightful talk. We have time for a few questions.
Hello, sir. Thanks for the talk. Here you used centrosymmetric crystals. Is there will be any changes if we are using non-centrosymmetric crystal during splitting?
Yeah, so basically, if you are using, so what happens is that if the system is non-centrosymmetric, you already do have a Rashba splitting, essentially, okay? So the effect of phonons will be minimal, if you see what I mean.
Okay. And
so you cannot tune it, essentially.
And also one more question. Why in parity and time reversal system, this effect is forbidden?
So the reason is that I'll try to, so it's just a simple simple quantum mechanics. Basically, in those systems you have that if you take, if you do a calculation and you have the two spins of a given band of a given wave vector, those give you the same energy, simply because you have immersion symmetry that causes this symmetry here, and time reversal gives you that. So if you combine them, you get this degeneracy. It's just a very elementary rule of solid state.
Thank you. Thank you.
Okay, thank you. Simple question on the Hamiltonian, slide number 9. What is the assumption to ignore the Coulombic type of interaction?
Sorry, I didn't catch it. So on this Hamiltonian?
Yeah, you ignore, I think, Coulombic type of interaction here.
Coulombic type of interaction, that's what you're asking?
Yes, why you ignore that? What is the assumption to ignore that kind of interaction?
So so this is only the part that's to do with the essentially spin phonon coupling, okay? So the idea is that if you have other interactions in the system, you take care of those separately, all right? Suppose you do your best possible calculation, I don't know, GW or the MFT, so then this happens afterwards, right? So the question is, if you now incorporate spin phonon effect, can you have splitting or not, right?
Okay, the other one, phonon, I think, behave like bosons. So how you deal with symmetry and anti-symmetry case?
So what do you mean? So so
you consider phonon as a boson, right?
Yeah.
So I think he shows symmetry, how you capture symmetry and anti-symmetry case for phonon.
So the what is symmetric or anti-symmetric is the, so I don't know if I have here. So it's basically the vibrational eigenmode. Okay. So the vibrational eigenmode, like the electron wave function, could be either so at the gamma point in a central symmetric crystal can only be either even or odd, right? So it is not the boson itself; it's the polarization of the phonon essentially that has this spatial property.
Okay, so I think in the interest of time, we should continue. Maybe we can continue asking questions in the break. Let's thank the speaker again, and I'll ask the next speaker to come forward. So our next speaker is Max Stengel from Instituto de Ciencia de Materias de Barcelona. And he will talk about first principle calculations of flexoelectricity. And I hope that the computer setting works this time.
Okay, sorry.
No problem.
Here, yeah.
Let's hope it works.
Yeah.
Okay, I'll do it.
Okay.
I'll do it by hand. Hello, everybody. Good afternoon. Sorry for the delay. My name is Maximiliano Stengel from Barcelona. My talk will be about two topics today. One is flexoelectricity and the other is long-range Coulomb interactions. So you might wonder what these two topics have to do together. and the link between the two is given by spatial dispersion. So I will essentially present the developments that we brought forward in the past few years in our group to make it possible to calculate from first principles spatial dispersion effects, which is essentially considering not like you have an electric field, you have the response to an electric field, which is the macroscopic dielectric constant. Here we are talking about non-homogeneous perturbations, which are modulated in space at some wave vector q. And instead of the macroscopic response, which is given by this P0 here, I will be focusing on the first order in Q, which is corresponds to the response of the gradient of the perturbing field. This is an outline of my talk. It's pretty simple. Let me start with flexoelectricity first. So you all be familiar with piezoelectricity, which is the macroscopic polarization response of a crystalline material to some uniform strain. This is a third-rank tensor, which requires inversion symmetry to be broken at the level of the crystal. These materials tend to be expensive, tend to be toxic sometimes. So we want to get away around that. And one of the possibilities that were being considered is flexoelectricity. Flexoelectricity is the polarization response to a gradient of the strain field, for example, when you bend the sample in the cartoon here. So this is a bending deformation. This doesn't work either. So this is a fourth-rank tensor this time, getting complicated, but it is a universal property of all materials, be it cubic or whatever symmetry you wish. And it has an interesting property that it scales with the inverse of the sample size. There's so much curvature you can put into a thick sample, and this makes it very relevant at the nanoscale. So why does it matter? Why are we interested in it? One reason is as a replacement for piezoelectrics, as I said. Other reasons are related to nanotechnology. For example, the possibility of writing information mechanically by switching the domains of a ferroelectric material. And then there are many other applications of flexoelectricity. I'd like to mention some new developments in the context of the interaction of light and strain gradients, which have been carried out recently. But essentially, this talk will not be focusing on applications. It will be mostly about the fundamentals of the effect and how we are able to calculate it from first principles. So why do we need first principles, first of all? So imagine an experiment where we bend a sample and we measure the voltage or the transient current that passes through the sample in short circuit. The issue is that we have many contributions which are coming from the bulk of the material, from the surfaces, from the defects, domain walls, and so on and so forth. Experimentally, we have only one number, which is the total current collected at the electrode, and so we cannot single out the individual effects. Obviously, we can do that with our theoretical microscope. And so it is interesting to try to get a first principles theory of this. We have a problem that we haven't encountered before in the theory of linear response in materials, which is that translational symmetry is broken. This is a pretty general question that arises when you consider spatial dispersion effects. And you will see that while we are focusing here on flexoelectricity, in reality, we are addressing a much broader class of problems where the perturbation is not uniform in space. And these tools will allow us to address precisely this kind of situations. So in the case of flexoelectricity, the idea is to work with acoustic phonons. And the acoustic phonons is obvious while I'm choosing it because it is a modulated displacement field or a deformation wave. What do we do with acoustic phonons? We look at the polarization response in the long wavelength limit, and at the lowest order we have essentially 0 at in the uniform case, just because an acoustic phonon at Q = 0 is a rigid translation of the whole crystal, and because of the acoustic sum rule, the polarization vanishes. At first order in Q, we have a gradient of the displacement field, which is a strain, and so we have the piezoelectric response of the crystal. And at second order in Q, finally, we find flexoelectricity. So by varying the direction or the polarization of the acoustic phonon and the propagation direction, I can in principle access all components of this fourth rank tensor. However, the details are a bit more complicated because we need to learn how to deal with this linear response problem in the context of the electronic structure methods we have. And so we'll have a number of problems to solve that are methodological, but at the same time conceptual. So we'll start from an expression like this, where we define the response to the acoustic phonon at some finite wave vector Q, and we can decompose the response into a clamped ion contribution at frozen ions, just the elastic wave, plus some contributions from the internal relaxation of the atoms in the cell in response to the macroscopic deformation. This is something that can be done very nicely with density functional perturbation theory, because we can factor out the phase of the modulated phonon and work with periodic functions, and so treat the linear response problem at the level of the primitive cell. However, there are many things that I don't know in this equation, which is, for example, how to define the electronic polarization response at finite Q, and how to treat the acoustic phonon perturbation. So this is the first part of the problem, dealing with the response at finite Q. And of course, the second part of the problem is to find a method to deal with the long wave expansion in the wave vector Q to capture piezoelectricity at first order and flexoelectricity at second order. So let me start with point 1A of this list of this to-do list, which is how to define the polarization response to an arbitrary perturbation that is applied at some wave vector Q modulated in space. So I will start from the usual assumption within adiabatic perturbation theory that the derivative of the polarization with respect to the perturbation amplitude is just the derivative of the current that is adiabatically induced with respect to the velocity of the perturbation. So the first idea is, well, we have the Berry phase, we know everything about the polarization, right? But actually here we have a modulated polarization response, so we cannot use a macroscopic quantity, which is the Berry phase. Well, the idea is, of course, we all learned in quantum mechanics what is the current density, so why not write it like this, which is the usual textbook formula. However, there are some technical issues with pseudopotentials. So in the end, what we end up doing is first defining a coupling between the Hamiltonian and an external vector potential, which is in general inhomogeneous in space. And then we define our current density as a derivative of this Hamiltonian with respect to the amplitude of the vector potential. And this is general. This works also in the context of non-local pseudopotentials. Let's get a bit more specific in the context of density functional perturbation theory. So we do the same all over the place, all over again, but with more nastier formulas. First of all, we write the derivative of the polarization with respect to the perturbation as a second derivative with respect to two perturbation, second derivative of the energy with respect to the electric field and the perturbation by using the thermodynamic relationship between P and E. And then by using this adiabatic perturbation theory, we move to an expression where the response function is defined as a Berry curvature of the first order wave functions in the vector potential and the first order wave functions with respect to lambda. So the first order wave functions to the vector potential have some nice properties in the long wavelength limit. At order q equals 0, they are trivial. They are just the derivative in k of the block orbitals. They start becoming interesting at first order in q, where they reduce to the second order derivative in k plus the response to an orbital B field. And we started noticing something that dispersion properties naturally lead to orbital magnetism, just because the dispersion of the polarization includes an antisymmetric component that relates to the orbital, to the coupling to an orbital B field. But the most important thing for our purposes is that this definition of the wave function response to a vector potential satisfies charge continuity. So we can use it for dealing with flexoelectricity, which is focusing on the electrical response and so on the charge density. So we're done with the polarization. Let's get to the acoustic phonons. It is interesting for many reasons that I hope will become clearer in the next few slides, to treat an acoustic phonon not as it is done usually, which is as some atoms that are displaced from their equilibrium position in the Cartesian frame of the crystal at rest, but as a true deformation of space, which means that I leave my atoms where they are in their original locations, but what I change is the coordinate frame by operating a coordinate transformation and redefining my quantum mechanical problem in curvilinear coordinates. How do we do that? Well, first of all, we start from some basic definitions like the metric tensor of the deformation, like the transformation. This was all known since the work of François Gégy on adaptive coordinates, and also the metric tensor formalism of Don Hammond. However, what we did, which is a bit different, is to apply it to the time-dependent problem. We need, I remind you that we need the time dependence because the polarization is the adiabatic response, so there is an implicit time dependence in this operation. It's interesting that we have that the frame velocity enters as an effective vector potential in the Schrödinger equation in curvilinear coordinates. And this has some interesting physical implications. For example, a uniform acceleration of the frame corresponds to an electric field. Imagine you take your atoms and you just accelerate them in space by letting the electron do whatever they want to do. And this, if you have a metal and you do it non-adiabatically, you will see that the carriers will just stay behind. And this simple picture allowed us to generalize the acoustic sum rule to the non-adiabatic case, which relates the sum of the non-adiabatic charges to the optical conductivity at the given frequency omega. We can play with this concept even further and have a uniform rotation, which is a magnetic field. And so this allows us to compute the rotational G factors in molecules. This is well known. If a molecule rotates, it generates a magnetic moment. And this is precisely done, accounted for by this vector potential in the Hamiltonian. But for flexoelectricity, actually, this is not really crucial, just because the magnetic currents are divergenceless. So they don't accumulate charge. They don't generate a potential that can be measured when you bend the sample. So we can safely forget about them for our purposes and just focus on the static Hamiltonian and expand it to linear order in the acoustic phonon amplitude. So what we find once we do, on top of this linear expansion in the amplitude, we do a long wave expansion in Q, we find that the Hamiltonian as at lowest order becomes, well, it vanishes at Q equals 0 just because a translation doesn't have any effect in the co-moving frame with, which is rigid with the atoms. And at first ordering Q, I recover exactly the uniform strain perturbation, providing a link between